dear students, I am Praveen, your chemistry educator. Students, in this video, what we are going to do, we are going to discuss the complete atomic structure chapter. Students, from the atomic structure chapter in the NEET examination, every year we get 3 to 4 questions, right? So those 3-4 questions you can easily do if you watch this video completely from the start to end, right? And also, you know that atomic structure, it is very much relatable from our daily life. Like whatever concepts are there in this chapter, you can see examples of those things in your daily life, right? So I will tell you that whatever concepts are there, how they are related in your daily life. Now, point is, after watching this video, you have to do certain tasks, right? What you have to do, you have to solve the DPPs that we provide in the description of the video. Also, those DPPs you can find on the PW app where lakhs of students are preparing for the NEET examination. So now students, first let's see that in today's session, what are the topics in atomic structure that we will be covering, right? So we will start with Dalton's atomic theory, because we get questions like statement types of questions in the exam from Dalton's atomic theory. Then we will talk about the subatomic particles, that means electron, proton, neutron and their properties. Then we will talk about the wave nature of electromagnetic radiation, and then the Planck's quantum theory. Then why we need Planck's quantum theory, right? Because there are certain phenomena like photoelectric effect and black body radiation. And then finally we will move into Bohr's model of atom, and after Bohr's model, in the Bohr model itself, we will talk about hydrogen spectrum, because hydrogen spectrum was explained by Bohr. Then finally, we will talk about like what are the drawbacks of Bohr model, and inside the drawback of Bohr model, we will talk about dual nature, where we will see what is de Broglie's equation and some questions from de Broglie's equation, and then Heisenberg uncertainty principle, and finally, we will discuss the quantum model, and within quantum model we will start with what are quantum numbers, right? How we do counting of number of orbitals and number of electrons in a given shell or subshell. Then we will talk about electronic configuration of atom, ion, then orbital diagram, then what are the shapes of orbital we have, and then finally we will talk about how half-filled and full-filled configurations are stable. So let's begin this chapter, and let's see first what is Dalton's atomic theory. So I hope you all know very well that Dalton was the one who introduced the term atom, right? Dalton was the one who said first of all that whatever matter you see around you, so every matter is made up of what? Atom. Or for every matter, the smallest unit is atom, right? So if you talk about Dalton's atomic theory, so we have certain points that we need to always remember, right? And you can memorize those terms in statement wise, right? Like the first point you can say in Dalton's atomic theory we have is matter is made up of tiny particles known as atom, right? Known as atom. Or you can also say like this, that atom is the building block, or atom is the smallest unit of matter, right? So this is according to Dalton. Now, matter or a smallest unit of matter is what? Atom. Now, apart from this, Dalton also said that atom is indivisible. Now, you know very well that we have already divided the atom. So, of course, there are drawbacks of Dalton's atomic theory. But currently, we are writing those points which Dalton gave, right? So, Dalton said that atom is indivisible, right? You cannot divide atom. Also, he said that atoms can neither be created nor destroyed, right? Atom is indivisible, as well as atom you cannot create or you cannot destroy. But apart from these points, which is regarding atom, he also said few points regarding the elements or the atoms of elements, right? What he said that when you take an element, students, so for one element, whatever types of atoms it has, all those atoms are identical, right? So if you take hydrogen, according to Dalton, what he said, that for the hydrogen element, whatever atoms of hydrogen we have, right, all those atoms of hydrogen will be identical in properties like size and mass, right? So that point here we can write it like atoms of same element, atoms of same element are identical in properties, identical in properties like size and mass, right? And at the same time he also said that atoms of different element, right, if you compare atoms of different element, so they will have difference in their properties. Like suppose if I take oxygen, if I take nitrogen, so if I take atom of oxygen and one atom of nitrogen and I compare, so definitely according to Dalton, the properties of oxygen atom will be different from the atoms of nitrogen atom. So I can write that point also, that atoms of different element will have difference in their properties, right? And apart from this, Dalton also said that atoms participate in chemical reaction, right? That point we still follow. We still believe that atoms are the base thing, atoms are the thing which will participate during a chemical reaction. So overall, if you notice, nowadays also we think like this, that whenever a reaction is happening, so during a reaction we are having only attachment or detachments of atom. So Dalton also said that atoms participate in chemical reaction, right? And one more point was there, right, which also you need to write down, that atoms combine in a simple whole number ratio. So that will be your last point in the Dalton's atomic theory, that atoms combine in simple whole number ratio, So these are certain points we have according to Dalton that he said regarding atom. Now of course nowadays if you notice, so most of the points are wrong now, because matter is made up of tiny particles known as atom. This point is true, but the tiniest particle, they are not atom, they are electron, proton, neutron, quarks, right? Atom is indivisible. We know that this statement is also false nowadays, because atom is divided into electron, proton and neutron. Atoms of same elements are identical in properties. Even this point is wrong if you look into the isotopes, right? Isotopes, they are the atoms of same element, but they have difference in the mass, right? And if you talk about isobars, so according to isobar, if you observe isobar, then the next statement is also wrong for Dalton, that is atoms of different element will have difference in properties. So atoms of different elements, even they can have some properties similar, like in case of isobars, right, they have the same mass number. And atoms participate in chemical reaction. This point is absolutely valid till now. But again, the last point of Dalton, that is atom combine in simple whole number ratio, this is also wrong. It's not mandatory that atoms will always combine in simple whole number ratio. Like if you look into the molecules like CO2, H2O, so for CO2, H2O, CO, NO2 type of molecule, this point is valid. But if I consider larger molecules, like suppose if I consider glucose, right? Or if I consider sucrose, right? So in case of glucose and sucrose, these types of molecules, of course, the ratio of carbon atom, hydrogen atom, oxygen atom, it is like 12, 22, 11 or 6, 12, right? 6, not 12, here it should be 6, yeah. So glucose C6H12O6 or sucrose C12H22O11, these molecules, right, in them the ratio is not at all simple, correct? So of course, no doubt in that most of the point of Dalton's atomic theory is wrong nowadays, but point is, you will be getting questions from this topic. And in the question, they will always mention that you have to answer according to Dalton's theory, right? So I hope you have noted down these points. So after introduction of Dalton's atomic theory, now let's talk about some of the fundamental terms which we require in this chapter, right? And whose meaning you should know. And I think these terms like isotope, isobar, isotone, isoelectron, right? You must have discussed in the mole concept chapter as well, right? Because there also you talk about these terms. So what is isotope? I hope all of you know very well what is isotope, right? Isotope, they belong from same element, right? So atoms, right, which have same atomic number, but different mass number, Like if you talk about carbon as element, right? So carbon has two common isotope. One is C612, one is C614. So in these two atoms, if you compare, so because they are from the same element carbon, so definitely they have same atomic number, which is 6, but they have different mass number. One has mass of 12 and one has mass of 14. So those atoms which have a same atomic number, but they have different mass number, they are your isotopes. And isobars, they are completely opposite of isotopes, students. Isobar means those atoms which have same mass number, but different atomic number. Now definitely, if atoms are having different atomic number, that means they are different element. But still they have same mass number. Like suppose if I consider the same isotope of carbon, C614, and I compare that with nitrogen, N714. So carbon, nitrogen, these are different elements. That's why they have a different atomic number. For carbon, atomic number is 6. For nitrogen, atomic number is 7. But for these two particular isotopes, the mass numbers are same. Both of them have mass of 14. So these two will be called as what? Isobars. Similarly, if you talk about isotone, so isotones are those atoms which have same number of neutrons, right? So isotone is a very simple term. If two atoms are there and they have same number of neutrons in the nucleus, so they will be called as what? Isotone. And similarly, if you talk about isoelectronic, right? So iso means what? Same, and electronic means what? Electron. So those species which have a same number of electron, they will be called as what? Isoelectronic species. So I hope that you all are clear with these basic terms like what is isotope, what is isobar, what is isotone, and what is isoelectronic. Now moving further, after understanding these terms, now let's talk about some of the history of atom. I hope the history of atom you people have studied already in your 9th class, right? In 9th class, you have the discussion of Thomson model of atom, Rutherford model of atom, Bohr model of atom, and how those fundamental particles like electron, proton, neutrons, they were discovered. But let's quickly do a recap of these topics, right? Regarding the fundamental particle and the history of atom, right? Let me tell you one thing. For the NEET examination, from this chapter, the main points, the main portions are Bohr model, dual nature, and quantum model. And that's how you can study this chapter. You can do it like this. Divide the whole chapter into 3 parts. One part will be completely Bohr model, one part will be what? Dual nature, and one part will be your quantum model. So in 3 parts you can study the chapter. And these are the backgrounds of the chapter. So first of all, if you talk about electron, right? Electron is one of the fundamental particle which is present in your atom. But if you talk about discovery of electron, so you must have heard this, you must have, I think, learned this, that electron was discovered by cathode ray experiment. And this experiment was performed by Sir J.J. Thomson, right? And how he performed this experiment, so here we have a setup for that experiment. He took a glass tube, right? And that glass tube you also call it as a discharge tube. Sometimes the same discharge tube is also called as Crookes tube, because Crookes was the scientist who designed this glass tube. So you can call it cathode ray tube, you can call it discharge tube, you can call it what? Crookes tube. Now, in this Crookes tube, discharge tube, what we do, we have fitted two electrodes, or you can say two metal plates, right? One left side, one right side. One of the metal plate, it is connected by the negative terminal of the power supply, and the other electrode or other metal plate, it is connected by the positive terminal of the power supply, right? The plate which you have connected from negative terminal will be called as cathode, and the plate which you have connected by positive terminal, that will be called as your anode, right? Now, point is, when you switch on the power supply, something happens between your cathode and anode. Now, definitely what happens there, right? You cannot see that immediately from your naked eye, right? But how you can see that? If you put a fluorescent screen behind the anode, like this experiment, when initially it was performed, right? So what we did, behind the anode, we kept a fluorescent screen. Fluorescent screen is made up of zinc sulfide, and that fluorescent screen or zinc sulfide screen was placed behind the anode, right? So when we switched on the power supply, what we noticed that that fluorescent screen is glowing. It is having a bluish green appearance, right? So when your fluorescent screen is glowing with some color, bluish green, that means what? Something is coming from this cathode side, right? And it is hitting your zinc sulfide screen. It is hitting your zinc sulfide screen. And that something, right, which is coming from cathode side, we named it as what? Cathode rays. We named it as what? Cathode rays, right? But see, we people already know electron. So we can understand like this also, that from cathode side, whatever particles are getting ejected, which is striking the zinc sulfide screen, that particle is nothing but your electron, right? So cathode ray is basically nothing but streams of electron we have, right? And that stream of electron is striking your zinc sulfide screen. That's why you are observing color there, right? Also, before in this setup, of course, in between the electrodes, what you do, you put air or any gas at low pressure. Low pressure is very important here, because when you will keep low pressure, then only you can easily discharge the air or whatever gas you have filled between the electrode. And also when the pressure will be low, that means between the electrodes, the number of molecules of air or whatever gas you have filled, like you can fill helium, hydrogen, different types of gases here. So if you put the gases at low pressure, then the number of molecules of the gas particle will be low. And when number of molecules will be low, so it will have a higher mobility, right? The electrons, the cathode ray can easily pass from cathode to anode, right? Also, if you talk about the power supply, so this power supply is more than 10,000 volt. 10,000 volt is a big voltage, right? But the power supply is nearly or greater than what? 10,000 volt. But see, overall point is, from this cathode ray tube experiment, right, we got what? Cathode rays. And later on, we concluded that in cathode ray, electrons are present. In cathode ray, whatever thing is present, that thing has mass, that thing has charge. And then later on, we named that thing as what? Electron. And of course, I hope you should know and you should always remember some of the properties of electron throughout the chapter. Like at least the mass and charge value of electron you should remember, right? The charge of electron is how much? The charge of one electron is 1.6 into 10 to the power minus 19 coulomb. And if you talk about the mass of electron, so it is nothing but 9.1 into 10 to the power minus 31 kilogram, right? So charge of electron is this and mass of electron is this. You need to remember this. Although like when you will be doing numerical questions, so in the question part, they will give you the values. But still, for your practice purpose, you need to remember these values of charge and mass of electron. And that's how from the cathode ray experiment, we discovered electron, not we, G.G. Thomson discovered what? Electron. Now, in the same way, the way we discovered electron, in the same way, or you can say in the same setup, proton was discovered, right? Proton was discovered by Rutherford and Goldstein, both of them. We gave credit to them, right? So, in discovery of proton, we had the same setup of a discharge tube, cathode ray tube, right? Same setup. We have the same glass tube, we have the same electrodes, right? We have the same power supply, everything is same. But the only difference is, during the discovery of proton, the cathode we had, that cathode was perforated. Perforated means in cathode we had some small holes, right? And why we created holes here? So that the protons or the nucleus, right? The protons or nucleus can easily pass through that cathode. And in cathode ray experiment, the zinc sulfide screen, the fluorescent screen, we kept it behind anode, right? But during the discovery of proton, the fluorescent screen or zinc sulfide screen, it was placed behind your perforated cathode. And here also it was glowing, right? So, if something is glowing behind the cathode, that means what? That means what? Something or some particle is coming from the anode side, right? And it is striking the fluorescent screen, which is placed just behind your cathode. And in this case, the particles which is striking, it is either your proton or a nucleus. Like suppose in this tube, if I fill hydrogen gas, so you people already know one thing, that hydrogen has a proton in it, in the nucleus, right? And it has an electron in it. So when you apply power supply, hydrogen will ionize, the electron, proton, they will separate. And in case of hydrogen, these protons will travel, right, from the perforated cathode. But suppose instead of hydrogen, if you take helium gas, right? So in the nucleus of helium, we don't have only proton, right? In the nucleus of helium, we have proton as well as neutron. And here we have two protons. Here we have what? Two protons. So if you fill helium gas in this tube, then in that case, from this perforated cathode, the nucleus of helium will travel, right? So that's why we say that in case of anode ray, because here whatever is traveling, it is coming from the anode side. So these rays, we name it as anode ray. And we also say that anode rays, they depend on nature of the gas. Anode ray depends on nature of the gas that is filled in the discharge tube. But if you talk about cathode ray, right? Cathode rays, they don't depend on nature of gas. Like whether you put oxygen, hydrogen, helium, you put any gas in this discharge tube, the property of cathode ray or the charge or mass of cathode ray, it is independent of gas. Why? Because in case of cathode ray, electrons will travel, and each and every electron of any atom, they are identical regarding their mass and charge. But if you talk about anode rays, right? So in case of anode rays, you have seen that nucleus will travel, and different gases, they have different number of protons in the nucleus. So definitely they will have different charge, different mass in the nucleus, right? That's why for different gases, different nucleuses will travel, and the nature or the charge or mass of the anode ray will differ, right? This is a very important point. Sometimes you get this in your assertion reason type questions, correct? Now, whether it is anode ray, cathode ray, both of them, they travel in a straight path. They travel in a straight line. And they will be deflected, they will be deviated when you apply electric field or magnetic field to it, because both of them, they have charge and mass, right? Now, in the discovery of proton part, you need to remember here one thing, right? The charge and mass of proton, because that's what you need later on in this chapter, right? So, charge of electron, it is again equal as charge of proton, right? Charge of proton, it is again equal as charge of electron. Only the nature are opposite, right? For electron, we say that it has negative charge, but for proton, we say that it has a positive charge. But the magnitude of charge is same. Charge of one electron, charge of one proton, both is 1.6 into 10 power minus 19 coulomb. But we have a huge difference in the mass part, right? The mass of proton is nearly 1.66 into 10 to the power minus 27 kilogram. And the mass of electron was of the order 10 to the power minus 31 kilogram, right? So there is a huge difference in the mass of electron and proton, right? So this is what we have in the discovery of electron and proton. Okay, just like electron, proton, we have also discovery of neutron, and neutron was discovered by none other than James Chadwick, right? But you don't have to go into the discovery of neutron part. Just remember that neutron was discovered by James Chadwick. But overall, what you need to remember here, the basic properties of electron, proton as well as neutron. The basic properties of electron, proton and neutron you need to remember. Now, after discovery of electron, proton and neutron, we have to quickly discuss, right, the models that were given. Like the very first model of atom we have is nothing but Thomson model, and Thomson model is completely based on your cathode ray experiment. Cathode ray experiment was done by J.J. Thomson. So at the same time, J.J. Thomson proposed his own model, and that we call Thomson model of atom. And his model was very simple. Thomson said that atom is spherical. Atom is spherical. Inside atom, electrons are embedded inside it, right? And the rest part of atom, he said, is positive. So according to him, according to Thomson, atom is spherical. Negatively charged electrons, they are embedded inside the atom, and the remaining part of atom is positive, is positively charged. And also he said that overall the atom is electrically neutral. Thomson also said that an atom will be always electrically neutral. Means what? Means whatever total positive charge we have inside an atom, that will be exactly equals to the total negative charge inside the atom, right? So that is your Thomson model. But of course, we know that this model failed, right? And you people already know that positive charge is not distributed throughout the atom. It is present in a very, very small region of atom, right? And that point was proposed by Rutherford, right? The next model, right? After Thomson model, the next model we had is Rutherford model, right? And again, just like Thomson, Rutherford model is also based on an experiment, and I hope you know very well that experiment was alpha ray scattering experiment. Alpha ray scattering experiment. Remember in your 9th class, you take a gold foil, a very thin sheet of gold. Gold atoms are very large in size. You bombard alpha particles on it. Alpha particles are nothing but your helium nucleus, helium 2 plus ion. When you bombard alpha particles on gold foil, right? So most of the alpha particles, they pass as it is. Some of the alpha particles gets deviated when they pass from near the nucleus, and very rare, 1 out of 15,000 alpha particle was reflected back on its own path. So see, what's the point? When Thomson said that positive charge is distributed throughout the atom, right? So Rutherford tried alpha ray scattering experiment just to check that point. In reality, if atoms has a positive charge throughout the atom and you are hitting the atom with alpha particle, helium 2 plus particle, So these particles are also positively charged. If throughout the atom we have positive charge, then what should happen? All the positive particles, they should get deviated. All the alpha particles, they should get deviated if positive charge is distributed. But that's not the reality. In reality, what happened? Most of the alpha particle, right, it passed in a straight line. That means what? Most of the part of atom is empty, right? And the points from where these alpha particles were getting deviated, those are the points where positive charge is present. And that point later on Rutherford defined as what? Nucleus, right? So Rutherford basically just modified the Thomson model, right? In Thomson model, we used to say that positive charge is distributed in the atom. In Rutherford model, right, the conclusion was, if this is your atom, then positive charge is not distributed throughout. The positive charge is present in a very small space, in a very small volume, and that space where positive charge is present, or where all your proton neutrons are present, this region, according to Rutherford, we called it what? Nucleus. So you can say like this, like Thomson discovered what? Electron. So in the same way, Rutherford discovered nucleus or proton, and then he proposed his own model. Now in Rutherford model, the main point was, inside atom, on the center, in a very small region, we have positive charge, and that region is called nucleus. And the electrons, they orbit around the nucleus, right? We have the nucleus inside the atom, and electrons, they are continuously, right, revolving around the nucleus. That was your Rutherford model. Rutherford even compared atom with solar system. He tried to explain at that time by comparing atom with solar system. He said that just like your sun, right, sun is at center, and all the planets, they are moving around the sun. So in the same way, in an atom, at the center we have nucleus, and all the electrons, they are revolving around the nucleus. That was the point of Rutherford. Now, I hope you all know very well that even the Rutherford model, right, that was unsuccessful, because we have drawbacks in Rutherford model also, right? And the biggest drawback in Rutherford model, right, that we talk about is regarding the stability of atom, right? If you look into the Rutherford model, so according to Rutherford model, what he said that we have a nucleus inside the atom, and electrons, they revolve, right, in circular orbit around the nucleus. Now, the question is, if your electron, it will start doing continuous radiation, right? So very slowly, your electron will become more and more closer to the nucleus, right? If your electron does continuous radiation, then very slowly electron will lose its energy, and slowly it will come close to the nucleus. And after a certain time, the electron should collapse, should collide in the nucleus. And if that will happen, your atom will be destroyed. But we all know that atoms are stable, right? Atoms are stable. So Rutherford was unable to explain this point, right? Rutherford was unable to explain. We can write it as a statement form. Like, what is the major drawback of Rutherford's model? The major drawback was Rutherford was unable to explain stability of atom or electron. Stability of atom or electron. Now, definitely, the stability of electron or atom was later on defined, or you can say stability was explained by Niels Bohr, right? And that's why after the Rutherford's model, the next model we have to discuss is nothing but your Bohr model. But students, before we start Bohr model, we need to learn regarding the background of Bohr model, right? Before going into Bohr model, after Rutherford's model, we have to discuss regarding the wave nature and particle nature of energy, right? So starting with the wave nature of energy. I hope you all know very well that what is the meaning of electromagnetic wave, right? Electromagnetic waves are radiated due to oscillation of electric field and magnetic field, right? So in this diagram, if you notice, suppose that along this axis, which I have highlighted in green color, along this axis if your magnetic field is oscillating, right, and along this axis, right, if your electric field is oscillating, right. So in these two directions, if your electric and magnetic fields are oscillating, then perpendicular to that, in this direction, right, you will be having radiation, right, or formation of your electromagnetic wave. But the point is, for electromagnetic wave, we have two different approach, we have two different concept, right? The classical concept is, or the earlier concept is, we used to think that electromagnetic waves, they are continuous in nature, and that continuous point was given by Maxwell, or that is also called as Maxwell theory of wave. And with the Maxwell theory of wave, where we used to say that in wave energy is continuous, you can explain some phenomena like interference and diffraction, right? Interference and diffractions. Interference and diffractions, these are some of the phenomena we observe for the electromagnetic radiation, electromagnetic waves, right? And these phenomena, they can be explained by the Maxwell theory or older concept of wave, in which we used to say that electromagnetic radiations, right, they transmit in a continuous fashion, continuous, right? Now, of course, we have another theory for electromagnetic wave, that is Planck's quantum theory, and there you say that energy in wave is transmitted in a discrete packets, but we will see that later on. Before that, we need to understand some of the parameters of wave. I hope you must have heard regarding the parameters of waves like wavelength, frequency, energy, wave number, time period. So first, let's try to understand those parameters and what do they mean in the electromagnetic wave. See, suppose if a EM wave is oscillating like this. So if you notice, starting from point A, if I assume that from point A it is a starting oscillation, so at point B, I can say that you are having a complete oscillation, right? From point A to B, you can notice that this is one oscillation. Now, point is, whatever time required to complete one oscillation by the electromagnetic energy, by the electromagnetic wave, that time, students, you call as time period. That's the first parameter we have, right? So if your wave is oscillating, so in one oscillation, right, when it will go from point A to B, so in one oscillation, whatever time it will take, right, tau, suppose it is tau second, so that time itself is called as time period of the wave. This is nothing but time period. Time period. This is the first parameter we have. Now, after time period, we have another very interesting parameter of EM wave, and that is wavelength. And it is quite similar to that of time period. See, from point A to B, I can say that one oscillation is happening, right? From point A to B, one oscillation is happening. Now, in one oscillation, whatever distance covered, whatever displacement is covered by the wave, that is your wavelength, right? From A to B, you can observe that we are having one oscillation. And in one oscillation, suppose that your wave is traveling how much? Lambda meter. Your wave is traveling how much? Lambda meter. So lambda meter is your wavelength. Lambda meter is your wavelength. So tau is time period, lambda is your wavelength, and wavelength is length of one oscillation, time period is time taken in one oscillation. Now, apart from these two parameters, that is wavelength and time period, we have a third parameter here, which is called frequency. Frequency is denoted by nu, right? And according to definition, if you see that what is the exact meaning of frequency, So frequency is related with number of oscillation, right? Students, please focus here. In one oscillation, whatever time it takes is called time period. So we can say this statement in reverse format, right? We can say like this, that in tau second, right, the wave is having one oscillation. Now if I count what is the number of oscillation in 1 second, right? So that can be done by unitary method. I can write it down like this. In tau second, we are having one oscillation. So in 1 second, the number of oscillation will be 1 by time period. Now this 1 by time period is your frequency. So we can define frequency like the number of oscillations by wave in 1 second is your frequency. The number of oscillation by the wave in 1 second per second is nothing but your frequency. And the unit of frequency will be, because it is 1 by time period, so unit of frequency will be either per second, or we also call it hertz. We also call it hertz, right? And one more parameter is there which is very important apart from time period, wavelength and frequency, and that is wave number. That is wave number. And your wave number is denoted by nu bar. Nu bar. And the definition of wave number is quite similar to frequency. Students, frequency is number of oscillation per second. So similarly, wave number is number of oscillations per meter. So wave number is defined with respect to length. Now again you can notice that I told you in one oscillation whatever distance is covered, that is lambda meter, that is your wavelength. So I can say the same statement in reverse manner. I can say it like this. In lambda meter I am having one oscillation. So in lambda meter if I am having one oscillation, so in 1 meter I will have 1 by lambda oscillations, right? So in 1 meter the number of oscillations are 1 by lambda. So this 1 by lambda term is nothing but your wave number. 1 by lambda term is nothing but your wave number. And again if you talk about the unit of wave number, right? So because it is 1 by lambda, and for lambda the SI unit is meter, so automatically for wave number the SI unit will be per meter, and in CGS you can write it as per centimeter. So these 4 parameters are very important for you: wavelength, frequency, time period and wave number. Also we have relation between these parameters, right? At least the relation between wavelength and frequency you need to remember, and that can be done in a very simple way by distance time relation. Just observe one oscillation, all of you, just observe one oscillation, right? From point A to B, right, I am having one oscillation. In one oscillation the distance covered is lambda meter, the time taken is tau second, and you know that speed is nothing but distance by time. So even if I apply that formula, I can say that speed of this wave in one oscillation is equals to distance traveled in one oscillation, which is lambda meter, divided by time taken in one oscillation, which is tau, right? So if I rewrite this, speed of the wave is equals to lambda, and 1 upon tau can be written as what? Frequency. Now this relation is very important for you, because sometimes you get direct question in the NEET exam from this formula, and that is very simple, right? Speed of electromagnetic radiation is equals to wavelength of the radiation into frequency of the radiation. And I hope you know that for all electromagnetic waves, like we have a classification of electromagnetic waves, right? Gamma, X, right? UV, visible, infra, micro, radio, right? But for all the electromagnetic waves, we assume that their speed is equals to speed of light, right? And this term is constant. The wave speed we always take as 3 into 10 to the power 8 meter per second, and this is also equals to speed of light, and even light is nothing but a type of electromagnetic wave, right? So this formula, especially speed equals to wavelength into frequency, you need to remember, right? Now, as we have understood the parameters of wave, and we have understood the history of atom, right? What is Dalton's atomic theory, what is Thomson model, what is Rutherford model. We have not started Bohr model, of course. So let's see few questions from the history of atom and Dalton's atomic theory. Can you all try this question by your own first? Take your pen paper. Like always try to do questions before me, right? So question is, select the correct statements from the following. So some statements are given and you have to choose which statements are correct, right? So I am solving it. You can pause the video and you can do it by your own. Later on you can match the answer. So if I read these statements, the very first statement is, atoms of all elements are composed of two fundamental particles. Now definitely this statement is not correct. We know very well that atoms, they are composed of not two fundamental particles but three fundamental particles, and they are electron, proton and neutron, right? Now if I read the second statement, the mass of the electron is 9.1 into 10 power minus 31. This is 10 power minus 31 kg. So of course I have told you in this session itself that mass of electron is 9.1 into 10 power minus 31 kilogram. So statement B is absolutely correct. Now if I read statement C, all the isotopes of a given element show same chemical properties. Isotopes, you know very well that isotopes have same atomic number, so they belong from the same element. Now because isotopes, they are from the same element, so that's why they will have same chemical property, right? Isotopes, they always have same type of chemical property, they just differ in the mass. So even the statement C is absolutely correct. Now proton and electron are collectively known as nucleons. Now this statement is absolutely wrong. See, nucleons means what? Nucleons means whatever particle present inside the nucleus. And inside nucleus, you know that we have proton and neutron. So proton and neutron, they are known as nucleons, but not the electron, not the electron. So definitely again, statement D is false here, right? And if you check the last statement, Dalton's atomic theory regarded the atom as ultimate particle of matter. Of course, according to Dalton's theory, if you see, so atom is the tiniest, smallest particle of matter. So according to Dalton, statement E is again correct. Now we have to select the correct statements only, and the correct statements are B, C and E. So B, C and E, they are present in your option C. So definitely in this case, your answer will be option C, right? Of course, it should be C. And the main thing is, this question we got in the NEET examination in the year 2023, right? In 2023, we got this question in the NEET exam. So even from the history part, the Dalton's atomic theory part, you get questions in the exam. And this is a very recent question, 2023, right? Now, let's do one more question, right? And this is from the parameters of wave theory. So, a particular station of All India Radio, New Delhi, broadcast on a frequency of, this question is from NCERT. If you read NCERT, in NCERT you will find this question. So, for a particular station of All India Radio, New Delhi, broadcast on a frequency of, so they have given frequency, this is 1368 kilohertz. The wavelength of the electromagnetic radiation emitted by the transmitter is, so it's a very direct question, right? Direct question. Frequency is given, speed of the light or wave is given 3 into 10 to the power 8, and we have to calculate wavelength. And just now I have told you that for wavelength into frequency is equals to what? Speed of light, yeah, speed of wave. So from here, if I calculate the wavelength, so that will be speed upon frequency. Now just substitute the values, right? Speed is 3 into 10 to the power 8 meter per second in the SI unit, and frequency, it is 1368 kilohertz, right? So if you convert into hertz, it will be 1368 into 10 power 3, kilo means 10 power 3 hertz, right? And if you divide, you will definitely get your answer, right? If I do rough calculation here, because I always do that, but you don't have to do rough calculation. You people have to do always the perfect, correct calculations, right? So 3 into 10 power 8 upon 1368 into 10 power 3. So this 10 power 3, if I take in numerator, 8 minus 3, it will be 10 power 5. So 3 into 10 power 5 upon 1368. Now if I take, let's say 1000 from this, so it will be 3 into 1000, 3000, and it will remain how much? 10 power 2 upon 1368. Right? If you divide this, it will be cancelled out some approximately 2 times. But 2 into 10 power 2, okay, all the answers are in 200 something, right? So it will be either 219.3 or 219.2. So we have to do calculation accurately here, right? Of course, the answer is B, that means 219.3. And I hope if you divide this, you will get your answer. I hope you all are doing this, right? If you divide, you will get your answer. But again, this question, which is a question of NCERT also, it came in NEET 2021 examination. So sometimes in our NEET examination, we get direct question from the NCERT part. Direct from NCERT. So you need to complete each and every question from the NCERT, right? Whether it is in text, whether it is the back exercise, each and every question. So now students, let's talk about the Planck's quantum theory. So we saw that what is the meaning of electromagnetic waves, right? And we saw what is the meaning of Maxwell theory. So in order to understand Planck's quantum theory, let's discuss both. Let's just compare the Maxwell's concept of electromagnetic wave along with the Planck's concept. See, the major difference is, according to Maxwell, if you go, so according to Maxwell, the electromagnetic radiations, they were continuous, right? According to Maxwell, what he suggested, that if you have a source from which electromagnetic waves are getting radiated, so these waves, they will be radiated in a continuous manner, right? But at the same time, the concept of Planck was completely different. Planck suggested that from a source, whenever electromagnetic waves will be radiated, so the radiation will happen in a discrete fashion instead of continuous. According to Planck, the emission will happen in a discrete manner. So there will be gaps. There will be gaps in the transmission. And you can see that these are nothing but your energy packets. These are nothing but your discrete energy packets, right? And these energy packets, Planck named them as quanta. And these quantas are nothing but photon in case of light. In case of light, the quanta term becomes what? Photon. So he said, Planck said that instead of continuous emission, right, the electromagnetic radiation, they will happen in a discrete way, right? And energy will be radiated in discrete packets, right? And also Planck said that energy of one quanta, energy of one packet can be calculated by the formula h into frequency, where h is your Planck's constant and nu is your frequency. So basically what he said, that for any quanta, the energy will be directly proportional to the frequency of the wave. And suppose E equals to h nu, so this h nu is energy of one quanta. Now if anywhere you have n number of quanta, right? So for n number of quantas, the total energy will become, the total energy for n number of quanta will become n times of h nu, right? Like in this example, suppose that I have just 3 quantas, right? So energy of 3 quantas will be 3 into h nu. Energy of 10 quantas will be 10 into h nu. So in general, energy of n quantas will be equals to n times of h nu, right? So Planck said that electromagnetic radiation will happen in discrete manner, right? And the classical concept according to Maxwell was that electromagnetic radiation happens in a continuous manner, right? And also according to Planck, we can calculate the energy of quanta, energy of wave from h into frequency. Okay, in the parameter part, you saw that we can directly relate this frequency with wavelength. So this energy formula can also be written in terms of wavelength. In terms of frequency, it is h into frequency. In terms of wavelength, if you write, So Planck's constant into, instead of frequency, we can write what? Speed upon wavelength. So energy of quanta can also be calculated by the formula hc by lambda. Right? And from these formulas, students, like h into nu, hc by lambda, you get direct questions in your examination. Now, the next point is, after Maxwell's theory of wave, after Maxwell's explanation of electromagnetic wave, we were able to explain some of the phenomena like interference and diffraction. But there were certain phenomena which we were unable to explain, and that's why Planck's quantum theory came. We had phenomena like photoelectric effect and black body radiation. So those photoelectric effect and black body radiation, right, we cannot explain them using the Maxwell's theory of wave. That's why we have the Planck's quantum theory, and with help of Planck's quantum theory, you can easily explain those effects. Like one of them is what? Photoelectric effect. So photoelectric effect is a phenomena which is explained by Planck's quantum theory. But for us, right, for NEET examination, this is a topic from which we get question in the examination. Now first let's understand what is the exact meaning of photoelectric effect. It's a very simple concept, very simple concept. You know what? Whenever you take a metal surface whose ionization energy is low, ionization energy low means what? From that metal, electrons can be easily ionized, electrons can be easily ejected. So if you take a metal whose ionization energy is low, and when you strike with electromagnetic radiation or photon or light, when this light strikes the metal surface, so as soon as light strikes the metal surface, electrons, they will absorb energy from this light, from this quanta, from this photon, and after absorbing energy, these electrons will be ejected. And that phenomena is called photoelectric effect. So if I try to define this in short, so in short we can write photoelectric effect as when light of certain frequency strikes the surface of a metal, electrons are ejected. And those ejected electrons, they are also called as photoelectrons because they are ejected by photon. So those ejected electrons are also called as photoelectron. So isn't it a very simple thing that you have a metal, right? Light is striking on that metal, and due to that energy, electrons are getting ejected. And that phenomena is called what? Photoelectric effect. Now the point is, this phenomena we were unable to explain completely with help of Maxwell theory, right? So we can explain this concept only on the basis of Planck's quantum theory, right? Let's go into the more detail of this photoelectric effect. Suppose if you want to observe the photoelectric effect, because electrons are not ejected directly, right? To get electron ejected, you need to make a proper setup, right? So if you do the proper setup to observe photoelectric effect, right, what you need to do, like you can take a tube, you can take a glass tube, in that you can connect two electrodes, one in the left side, one in the right side. Now here, if you notice, on the left hand side, we have electrode of that metal from which we want to eject electron, right? The metal whose ionization energy is low, the metal from whose surface you want to eject electrons, right? That metal we have taken on the left hand side. And on the right hand side, we have another electrode, and this is acting like an acceptor here. So when electrons will be ejected from the left electrode, those electrons will be accepted, right, by the right side electrode. And the right side electrode here, we are calling it anode, and this has positive charge because when it has positive charge, then only it can accept electrons, because electrons has what? Negative charge. And the left side electrode, we are calling it cathode, and it has negative charge because we assume that this metal surface, it is electron rich, right? And if it is electron rich, overall it will have negative charge, and because it is electron rich, it can eject what? Electrons. Now, these electrons will be ejected when light of certain frequency will strike on this. Light of certain frequency will strike on the metal. Now, if you make a complete circuit, what will happen? As soon as light will strike on the metal surface, electrons will be ejected. It will be accepted by the anode, right? And in the circuit, you will have a flow of electron. So when electron flows in this circuit, so then we understand that electron is getting ejected because of striking of light. If you find no deflection in the ammeter, that means no current is there in the circuit, that means no electron is flowing in the circuit. So that means in that case, electrons are not getting ejected. So this is the way you observe photoelectric effect in your laboratory. But now I hope at least you have understood what is the exact meaning of photoelectric effect, right? When light of certain frequency strikes the metal, right, electrons are ejected. Now, point is, if you observe this phenomena on atomic level, because we are dealing with atomic structure chapter, so on atomic level, what I can say, if this is your atom, this is your nucleus, right? So definitely there will be electron inside the atom. There will be electron, there will be loosely bonded electron inside the atom, right? Now, when your electron is present inside the atom, like when you say that electron is in atom. So when you say that electron is in atom, so that means in that case, electrons are getting attracted by the nucleus, because electron has negative charge, nucleus has what? Positive charge. So currently, when electron is present inside atom, electrons are getting attracted by the nucleus, right? Now, to remove this electron, I need to give certain amount of energy. And that energy here, in case of photoelectric effect, we are providing in terms of photon, So when photon or energy in terms of photon, it will come, it will strike the electron. So electron will absorb that energy and then it will get ejected. And here ejected means what? The electron will move away from the nucleus. And when electron will move away from the nucleus, the nuclear attraction will be less, and then you say that electron is in free state or electrons are getting ejected. So from this concept, we can also extract the formula of photoelectric effect, which you also called as Einstein's equation of photoelectric effect, and you people will get numerical questions from that formula. And see, that formula we can easily extract. Suppose, all of you suppose here that in terms of photon, the total energy we are supplying, it is E. The total energy we are giving in terms of photon, in terms of radiation, that is E. Now, electron, when it gets ejected from this atom, so before that, before getting ejected, before going into free state, it will absorb certain amount of energy. And that energy is called as threshold energy or work function. So you are giving total E energy, and suppose that electron, right, when it gets ejected, so during that it absorbs E naught amount of energy. So E energy you are giving, and out of that E naught energy is getting absorbed by the electron, right? So what is your remaining energy then? The remaining energy will be E minus E naught, E minus E naught. So now when your electron is in free state, so it can have a maximum of E minus E naught energy. E you have given, out of E, E naught is absorbed by the electron. So the leftover energy is how much? E minus E naught. So this E minus E naught energy, right, now it will have for the free electron, and that can be converted into the kinetic energy of free electron. And that's why we write that this E minus E naught will be equals to maximum possible kinetic energy. Why we write maximum here? Because of course there can be loss of energy in other ways, but total maximum kinetic energy we can achieve is E minus E naught. Now this formula, students, E minus E naught equals to maximum kinetic energy, is known as equation of photoelectric effect. And also you can write down this formula in different ways, in multiple ways. Just now you saw in Planck's quantum theory that energies can be written as Energies can be written as in terms of frequency or wavelength. So here also, if I write the energy in terms of frequency, so the same formula can also be written as, instead of E, I can write h into nu. Instead of E naught, I can write h into nu naught. And you all know that kinetic energy can be written as half into mass of electron into its velocity square. Right? Not only that, the same energy can also be written, expressed in terms of wavelength, right? In terms of wavelength, the same formula can be written as, instead of E, I can write hc by lambda, hc by wavelength, minus, instead of E naught, I can write hc by lambda naught, hc by lambda naught. And again, kinetic energy as half mv square, half mv square. So whether it is E minus E naught equals to maximum kinetic energy, whether it is h nu minus h nu naught equals to kinetic energy, whether it is hc by lambda minus hc by lambda naught equals to kinetic energy, all are same. They are just in different forms. And in your question, according to the question, you have to use these formula. In your question, if frequencies are given, then you need to use the second one. In your question is if wavelength is given, then you need to use the third equation, right? Also, I said that E naught is the amount of energy that is absorbed by your electron, right, when it gets ejected, and that is called as what? Threshold energy. This E naught term, students, this E naught term is called as threshold energy or work function, right? So just like E naught, if I am writing E naught as h nu naught, right? So if E naught is called threshold energy, then similarly this nu naught will be called as threshold frequency. And similarly, this lambda naught term will be called as your threshold wavelength. So I hope that you have noted down this formula, because from this only you will be getting questions in your examination, right? Now, apart from this, like what is photoelectric effect, then what is the equation of photoelectric effect, we have few more terms to discuss here, right? See, in photoelectric effect, there are 2 points which you get in your exams also directly, especially in the assertion reason type of question. So there are 2 points. First point is the kinetic energy of electron increases with increase in incident energy or frequency, right? So in photoelectric effect, when you increase the incident frequency, so by increasing frequency, incident frequency, your kinetic energy will also increase. And this point we can easily justify from the equation of photoelectric effect. Just now we have seen that the kinetic energy or maximum kinetic energy of electron is equals to h nu minus h nu naught. Now this h nu naught term is threshold energy, which is constant for metals, right? For each metal that term will be constant. The only variable parameter here is kinetic energy and this incident frequency, and they are linearly directly proportional to each other. If you increase this frequency value, if you increase this nu value, then this h nu value will increase. And if this will increase, this is constant, if this will increase, automatically your kinetic energy will also increase. Not only that, the same thing we can also explain in terms of graph. In terms of graph also, the same point can be explained, right? If I plot a graph by putting kinetic energy of ejected electron on the y-axis and incident frequency on the x-axis, then my graph will be straight line, because this equation, it is very similar to y equals to mx plus c, where kinetic energy is y, frequency is x, h is your slope, and minus h nu naught is your intercept. So because your intercept is minus h nu naught, that means whatever straight line I have, it will start from the negative side of y-axis, right? And the graph will look like this. Why we have created dotted line here? Because kinetic energy cannot be negative, right? Here the minimum value of kinetic energy will be what? 0. And if you notice the graph, so this is the frequency which is your nu naught, or this is your threshold frequency. Means what? If your incident frequency is equal to nu naught or greater than nu naught, then you can observe photoelectric effect, because then electron will be ejected. But if your incident frequency it is less than nu naught, if your incident frequency is less than the threshold frequency, that means it is in the left hand side graphically, in that case there will be no photoelectric effect. Sometimes you get question from this also, just a comparison between incident frequency and threshold frequency. So always remember that if your incident frequency is more than or equal to threshold frequency, then only you can observe photoelectric effect, right? If your incident frequency is less than threshold frequency, then you cannot observe photoelectric effect. And again, this point is very, very important for you, that when incident frequency is increased, so with that the kinetic energy of ejected electron will also increase. So this is the first point we have in photoelectric effect, which is important. Now one more point is there from which you get questions in the examination, and that point is number of ejected electrons will increase when intensity is increased. When intensity is increased. So point is, for the incident light, when you increase the intensity, so by increasing intensity, the number of ejected electron will increase. You will have more and more current, you will have more and more photoelectrons ejected. Now this particular point, you can explain only by Planck's quantum theory. And that's why I said that to explain photoelectric effect, we require Planck's quantum theory. Because see, if this is your metal surface, right? If this is your metal surface and you follow Planck's quantum theory, so according to Planck's quantum theory, what you can say? You can say that intensity of light means nothing but number of photons in a particular space per unit time. So per unit time, per unit volume, right? In a certain volume, whatever number of photons are there, that represent intensity. So more intensity means you have more number of photons, and less intensity means you have less number of photons, right? So when I say that I am increasing the intensity, that means I am giving more and more photons to the metal in same time, right? Now if I assume that one of the electron can be ejected by one photon. So the concept is like one electron will absorb one of the photon and then it will be ejected. So now you can understand, if I give one photon, so one electron will be ejected. If I give two photons, then two electrons will be ejected. If I give 10 photons, then 10 photons will be ejected. So if I increase intensity, that means I will increase number of photons per unit time, and if I increase number of photons per unit time, then automatically number of ejected electron will be increased. So this point of photoelectric effect can be explained only in terms of quantization of energy, in terms of quanta, in terms of photon. But again, for you people, from these 2 points, please note it down, because you will be getting questions from this directly in your examination, right? So this is one phenomena, photoelectric effect, which requires the knowledge of Planck's quantum theory. Apart from photoelectric effect, we also have another phenomena which is called black body radiation, and that black body radiation, it also requires the knowledge of Planck's quantum theory. So here again, first let's try to understand what is this exact mean. What is the meaning of black body radiation? See, it's a very, very simple concept. Like first it was observed by taking iron metal. First it was observed by taking the iron metal, right? What we observed, that when we take iron and we heat the metal, So when you continuously heat anything, so its temperature will rise, its temperature will increase. So by heating, when we increase the temperature of this iron, we observed a color shift. We observed a color shift. Like initially when we heated iron, we observed that it is emitting red color. It is appearing red color. If you increase the temperature further, then the color becomes more like orange, right? If you increase the temperature further, then the color becomes yellow. If you increase the color further, then it becomes white, and then further it becomes blue. So point is, when I change the temperature of this material, this iron, so by changing temperature, by increasing temperature, I can observe a change in color. Now this phenomena is called black body radiation. This phenomena is called black body radiation. Please do not get confused by black body, right? Black body, when you say black body, I think in your 9th, 10th class also, you must have discussed regarding black body. What is the meaning of black body? If an object is there which can absorb all types of electromagnetic radiation, and at the same time, when it has a sufficient energy, it can eject all types of electromagnetic radiation. So if there is an object, there is a matter, right? There is a particle which has tendency to absorb and radiate all types of electromagnetic radiation, then that object is called black body. And radiations from those type of object is called black body radiation. But we know that nothing is perfect black body, right? In practical world, whatever matter around us present, whatever matter is there, right? So they always absorb and radiate limited type of electromagnetic radiation. So even your iron is a black body. Of course, not perfect black body, right? But it is a partial black body. Everything around you which can do radiation, which can absorb radiation, is a partial black body, not a perfect black body, right? And that's why we named this phenomena as black body radiation, right? But here we have radiation from this metal. So point is, by increasing temperature, we can observe change in color, and that is your black body radiation, right? Point is, why this is happening? Why we are not observing just increase in intensity? Why not the iron is remaining red in color and only its brightness is increasing? Why it is having change in color? So that point can be explained in terms of Planck's quantum theory, right? Because see, in a simple word, in a very simple way, you can say like this: if I am getting different colors at different temperature, so that is possible only when these colors or their photons are discrete in nature. Their photons are discrete in nature, right? When you are observing red, so that means at that time, the red photons are having the maximum intensity, right? When you are observing yellow, so at that particular moment, the yellow photons have the maximum intensity. So see, whenever radiation happens, it's not like that only one color is emitted. A range of colors are radiated always, but the one whose radiation is higher, that color you see from your naked eye. Now, black body radiation, if you see this graphically, right? So here we have different curves. Now these curves are nothing but your radiation curves, right? If you see that we are having a shift in temperature here, change in temperature here, right? So at 7000 Kelvin, if you notice, so this is our curve, right? This is our curve at 7000 Kelvin. So point is, this is the radiation. Radiation always happens in a range, So point is, at 7000 Kelvin, the radiation is happening from this point to this point, from this wavelength to this wavelength, right? But out of all these wavelengths, at 7000 Kelvin, the intensity, right, we are plotting on the y-axis, the intensity is highest for this violet color. Can you see that? So at this temperature, in this radiation, I will have what? Violet color, right? Now, when I decrease temperature from 7000, if I go to 6000 Kelvin, right? So at the lower temperature, again, this is your radiation range. This is your radiation range. This is your radiation range. And out of this, if you notice, so at this point we are having the maximum intensity. So here the observed color will be bluish, right? At 5000 Kelvin, here is the highest intensity. So here the color will be what? Yellow. At 4000 Kelvin, this is the point where you are getting the maximum intensity. So at 4000 Kelvin, the observed color will be what? Red. Now what I said, for that iron, when I increase temperature, the color will shift from red to orange to yellow to white. Now that you can observe here graphically. At lower temperatures like 4000 Kelvin, I am having red color as highest intensity, right? Here yellow, and then it is becoming more bluish. So overall in graph also you can notice that with change in temperature, right, you will observe change in color. And that is your black body radiation. Okay, from this graph you can get two type of problem. One is a relation between temperature and wavelength. You know that red has the highest wavelength, right? And yellow has comparatively lower wavelength. So a relation you can observe here is when I increase temperature, the observed wavelength decreased, right? When I increase the temperature, the wavelength decreases. The graph or the maxima of graph shift towards left. So from this point, you will be getting direct questions in the examination. Temperature and wavelength relation. One more question you can get here between intensity, right, and wavelength. So you can say like this. When you increase your wavelength, if you go from left to right, your intensity will first increase and then decrease graphically. Right? So graphically I can say that when your wavelength is increased, so with wavelength, right, according to this graph, intensity first increases, then decreases. So in black body radiation, these 2 points are very, very important for you. Relation between temperature wavelength, temperature increases, radiated wavelength decreases, and relation between wavelength and intensity. When wavelength is increased at any particular temperature, intensity first increases and then it decreases, right? So now I think from this photoelectric effect, black body radiation and Planck's quantum theory, you can practice questions, right, from the DPPs that we are providing. But here now let us practice some of questions in this session itself, right? So take your pen paper again and try to do these questions with me, all of you, or before me if you want. So the very first question we have here is, when electromagnetic radiation of wavelength 300 nanometer falls on the surface of a metal, electrons are emitted with a kinetic energy of this much. What is the minimum energy needed to remove electron from the metal? Again, minimum energy needed to remove electron from the metal is nothing but your threshold energy. Minimum energy required to remove electron from an atom, from a metal, is nothing but your threshold energy. So in this question, they are basically asking to calculate the threshold energy. Now, the basic formula, you know, I hope you will easily remember that. The basic formula means E minus E naught equals to maximum kinetic energy, right? Now, write this formula according to the question, right? So, incident energy, they have not given directly, they have given incident wavelength. So, I can write this E in terms of wavelength, and this E can be written as hc upon lambda minus E naught. Leave it, because E naught we have to calculate. And kinetic energy, we can write it as half mv square. But in the question, they have directly given the kinetic energy value. So we can directly keep it as kinetic energy. Now just substitute the values. Students, the value of Planck constant, it will be given in the question, but you should remember also, it is 6.626 into 10 power minus 34 into c, speed of light, 3 into 10 power 8 divided by wavelength 300 nanometer. So if you convert nanometer into meter, it will be 10 to the power minus 9 minus E naught equals to kinetic energy, which is 1.68 into 10 power 5. I hope if you solve this, you will get your answer. Let me do it again roughly. So 10 power minus 9, in numerator it will become 9 plus 8, 17, and 10 to the power minus 34 plus 17 will become minus 17. So this is, let me write it here, this is 6.626 into, now that 10 to the power minus 34 has become 10 to the power minus 17 into 3, 10 power 8 I used it, upon 300 minus E naught. So here we have a question, right? You can also do it with me, right, or before me. Pause the video, solve it first, and then at the end you can match your answers. So the question we have is, when electromagnetic radiation of wavelength 300 nanometer falls on the surface of metal, electrons are emitted with kinetic energy 1.68 into 10 power 5 joules per mole. What is the minimum energy needed to remove electron from the metal? So first of all, we have to calculate minimum energy needed to remove electron. So students, minimum energy required to remove electron from the metal is nothing but your threshold energy or work function. So in this question, you have to calculate what? You have to calculate the work function of the metal, correct? Now, they have given incident wavelength and they have given the kinetic energy, ejected kinetic energy. But please focus on the value here. The kinetic energy is given as 1.68 into 10 to the power 5 joules per mole. So this kinetic energy is for 1 mole of electron. Now you know that 1 mole electron, basically it means 6.022 into 10 to the power 23. So instead of 1 electron, here they are talking about 1 mole of electron. So for these many electrons, the kinetic energy is this, right? Now, if you talk about the incident wavelength, so with help of incident wavelength, we can easily find out the incident energy or incident energy of the quanta, right? Incident energy E can be calculated as hc upon lambda, and value of Planck constant, it is 6.626 into 10 power minus 34. In round off, you can take it 6.63. In questions, they will give you the value of Planck's constant. Now, speed of light is 3 into 10 to the power 8 divided by wavelength. In nanometer, it is 300 nanometer. So, in meter, it will be 300 into 10 to the power minus 9. Now, if you solve this, the calculation is not at all difficult. It is very easy, right? 3, you can cancel 300 by 100 times, right? 100 into 10 power minus 9 will be 10 to the power minus 7. 10 to the power minus 7 in numerator, it will become 8 plus 7, 15. And 10 power minus 34 plus 10 to the power 15 will become 10 to the power minus 19. So this will be 6.626 into the all 10 power terms will become 10 power minus 19 joules, right? But this is the energy of one quanta, and one quanta can eject one electron. Now the kinetic energy is given for these many electrons. So what we can do here, we can calculate energy, right, of Na quantas, right? Energy of Na quantas or energy of 1 mole of quanta will be how much? It will be simply Avogadro number into energy of 1 quanta. That means total energy, total incident energy for 1 mole electron, it will be 6.626 into 10 to the power minus 19 multiplied by 6.022 into 10 power 23, right? If you multiply this, you will get your incident energy. Incident energy, if not for 1 electron, incident energy for 1 mole of electron. And then you have the kinetic energy of 1 mole electron. So from these two, you can easily calculate threshold energy of 1 mole electron by using the formula E minus E naught equals to kinetic energy, maximum kinetic energy. So from here, E naught can be written as total incident energy minus kinetic energy. So now you have to do just two things. From here, multiply these two, get the total energy, and from that, subtract the kinetic energy, you will get your threshold energy. So in questions, you need to focus on this point, that whether the values are given for 1 electron or whether the values are given for 1 mole of electron, right? So according to that, you have to solve. And if you solve this, ultimately, your answer will become 2.31 into 10 to the power 5 joules per mole, and this is nothing but your work function or threshold energy, right? And this question again we got in the NEET 2022 examination, right? So from photoelectric, especially from the formula E minus E naught equals to kinetic energy or H nu minus H nu naught equals to half mv square, from those you get questions in your examination, right? Now let's see one more question. Now this time it is from Planck's quantum theory directly. Calculate the energy in joule corresponding to light of wavelength 45 nanometer. Now Planck's constant is given here, 6.63 into 10 to the power minus 34 joule second, and speed of light is also given. So in this question we have to just find out energy, right? And wavelength is given. So we know the direct formula, right? Energy of wave can be calculated as Planck's constant into frequency or Planck's constant into c by lambda. So here, because lambda is given, I will write energy as hc by lambda. Now the value of h I have to take is 6.63 into 10 power minus 34. Value of c, speed of light, I have to take as 3 into 10 to the power 8 divided by wavelength is in nanometer, so I will have to convert that into meter. So 45 nanometer, it will become how much? 45 into 10 to the power minus 9. And I hope you can easily do the calculation here again. From 3 it will be cancelled out 15 times. So it will be 6.63 upon 15. And 10 power minus 9 in numerator it will become plus 9. So 8 plus 9 17, and 10 to the power minus 34 plus 17 will become 10 to the power minus 17. Energy in joules, right? If you want you can multiply with 100 here. So it will become 10 to the power minus 19. So it can be further rewritten as 663 upon 15 into 10 to the power minus 19 joules. If you divide this, it will be 40 something, right? Now we can divide this. It's very simple, right? It will not take much time. 15 fours are 60, right? Remainder 6, 3. Again 15 fours are 0.2. So overall it will be 44.2 into 10 to the power minus 19 joule. That will be your answer. Yeah, I wrote 44.2, you can write it 4.42 into 10 to the power minus 18, and unit is joule, right? So this is a very simple question from Planck's quantum theory or wave theory, and this question again we got in the NEET 2014 examination, right? So now I think after Rutherford model, you understood very well, right, about the Planck's quantum theory. And after Planck's quantum theory, you need to understand one thing. Overall, in a summary, you can say that energy can be transmitted in discrete fashion, right? Energy can be transmitted in discrete fashion in terms of quanta, in terms of energy packet, in terms of photon. So it's not necessary that your energy will be always continuous. Energy can be discrete. Now, why I am emphasizing this point? Because after Rutherford model, right, in Bohr model, the same modification has been used, right? If you remember, in Rutherford model, I told you that that particular model failed because we assumed that electron will radiate energy continuously. So continuously it will come closer to nucleus and ultimately it will collapse into the nucleus. But Bohr modified that point. Bohr said after Planck's quantum theory that radiation from electron again it will not be continuous. Instead of continuous, from electron also, radiation will happen in a discrete manner. In a discrete manner. And on this basis, Bohr created his own model, which we call as Bohr's model of atom. If you overall look into Bohr's model, so it is quite similar to your Rutherford model, right? In Bohr model also, you have the nucleus at the center of atom, right? Right? But the only thing is, Bohr said that energy is quantized, energy is discrete in atom, especially for the electron. So he created some discrete orbits, some imaginary discrete orbits around your atom, around your atom. And those discrete paths in which your electron will revolve, Bohr named those paths as your orbit. So in a sequence, you can say like this: in Thomson model, electron was discovered, right? In Rutherford model, we got discovery of a nucleus, proton, right? Similarly, in Bohr model, the biggest point is regarding your orbit, right? What Bohr said, he said that we have atom, inside atom we have nucleus, and in the surrounding of nucleus we have some, okay, when we draw this orbit on paper, it looks like planar, but in reality it's not planar. Assume that it is three-dimensional. These circular paths, they are three-dimensional, right? So around the nucleus we have circular paths, and in these circular paths only your electron will revolve. Your electron will revolve, and those circular paths he named as orbit, right? But from where he got this idea, right? From the discrete energy concept. Because if you say that electron can stay in this path, in this orbit, or this orbit, or this orbit, that means what? Electron cannot stay in between these orbits. And that is possible only when the electron's energy is not continuous, it is discrete. So either your electron has this energy value, or your electron has this energy value or this energy value. So there is a gap in the energy values, and in the values, if you have gap, that means it is discrete, right? Not only that, you know from your 9th class onwards that these orbits, right, we gave them name, Bohr gave them name, like the closest orbit from the nucleus, we call it first orbit, right? Then second orbit, then third orbit, and so on, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, up to infinity, right? And these orbits are alphabetically called as K, L, M, N, O, P, Q, R, like this. So this is your Bohr model, right? We have orbits, we have nucleus, and electrons continuously revolve in those orbits, right? So Bohr model finished here, right? No, not at all. Apart from giving this model, what Bohr did, Bohr calculated so many things about your orbit or electron, and from those things only you get questions in your examination, in your NEET examination. After understanding the basic idea of Bohr model about your orbit, right, what you have to do in Bohr model, you have to understand certain parameters that Bohr calculated. Of course, he calculated those parameters using classical concept, classical physics, but we get questions from that. Those parameters are, the very first one is angular momentum. I hope you all know from the physics what is angular momentum. Mass into velocity into r. Whenever something is having circular motion, so it will have angular momentum, and angular momentum is mass into velocity into r. So for electron, it is mass of electron into velocity of electron into r. What is r here? R is distance from nucleus. Suppose that if I consider the first orbit here, right? So electron is present in this orbit. So distance of electron or orbit from the nucleus is your r here. Distance of electron from your nucleus or orbit from your nucleus is your r here, right? So m into v into r, this is your angular momentum, and Bohr said that it will be always multiple of n. and if it is multiple of n, that means it is n times of h by 2 pi. H by 2 pi is a constant and n is your orbit number. Means what? For first orbit, it will be 1 into h by 2 pi. For second orbit, it is 2 into h by 2 pi. Right? And h is your Planck's constant, and h by 2 pi, students, you can also write it as h cross. H by 2 pi can also be represented as h cross, right? So n into h cross also can be written, right? After angular momentum, the second parameter he explained regarding your orbit and electron is radius of orbit. Radius of orbit. Or you can also say distance of electron from the nucleus. Now, for radius, he derived a formula which is 0.529 into n square by z, and unit is angstrom. When you calculate radius of orbit from this formula 0.529 into n square by z, so you will get your answer in angstrom units, right? And the third parameter he calculated, right, is total energy. Total energy of your orbit or electron, right? So total energy of electron in an orbit is equals to minus 13.6 into z square by n square, where n is your orbit number, z is your atomic number, whatever atom you are using, right? And if you calculate total energy from minus 13.6 z square by n square, from this formula, your answer will be in electron volts, right? And the last parameter we have here is speed or velocity of electron. And the velocity of electron can be calculated from 2.18 into 10 to the power 6 multiplied by z by n. Again, z and n are your atomic number and orbit number. And in this case, when you calculate velocity from this formula 2.18 into 10 power 6 z by n, your unit will be SI, meter per second. So point is, you need to first memorize these formulas in this part, because you will be getting direct formula based questions from this. Of course, I will tell you how we got this, how Bohr derived these formulas, but before derivation, before even deriving it, you need to remember it, because if you remember the formula, you will be able to solve the question, right? So for angular momentum, nh by 2 pi, radius 0.529 n square by z, angstrom, energy minus 13.6 z square by n square electron volt, right? And velocity 2.18 into 10 to the power 6 z by n, meter per second. Also, in energy terms, like when you say minus 13.6 z square by n square electron volt, so this is the total energy of your electron. And you know that total energy is equals to sum of potential plus kinetic energy. But if you remember total energy, from that only you can also calculate the potential and kinetic energy of electron, because the potential energy of electron is directly equals to the total energy, directly equals to the 2 times of total energy, not total energy, 2 times of total energy. So if your total energy is minus 13.6 z square by n square eV, then potential energy will be 2 into this, and kinetic energy is equals to mod of total energy. Means in total energy, instead of minus, if you put plus, so that will be the formula of your kinetic energy. So instead of total energy, sometimes we get questions from the calculation of potential and kinetic energy as well, right? So I hope that you have noted down these formulas, because from these formulas you will get direct question in your examination. Now let's see a quick derivation of these formulas, how he derived this. So according to Bohr model, if you go, you have the nucleus of your atom, and let us say that I have taken any of the orbit out of 1, 2, 3, 4, 5, 6, 7, 8, right? I have taken some nth orbit, and in this nth orbit, your electron is having circular motion, right? Now point is, Bohr explained the stability of electron, right? And he explained that according to centripetal and centrifugal force. What he suggested, that when your electron is revolving around the nucleus, right? So electron will be attracted by the nucleus, and that will act as your centripetal force. And whenever something is in circular motion, it will have some centrifugal force in the outward direction. And the magnitude of centripetal force will be equals to the magnitude of centrifugal force, right? And this is the base of all the derivations. All the derivations can be done from this point. Centripetal is equals to centrifugal. Now point is, in this case, centripetal force is the force of attraction of nucleus and electron. Now suppose in general, I have an atom whose atomic number is Z. So if atomic number is Z, in the nucleus, the number of proton will be Z. Charge of one proton is equals to the charge of electron. We represent that E. The value 1.6 into 10 to the power minus 19 coulomb, we represent that as E. So if I have Z protons, then the charge of nucleus, the total charge of nucleus will be Z into E. Z into charge of one proton, right? Now why I am talking about charge here? Because the force of electron and nucleus, it is a electrostatic force. Electrostatic force can be calculated as K into Q1 Q2 by R square, right? Charge of first particle into charge of second particle divided by R square. And that electrostatic force, students, it is acting as a centripetal force here. So centripetal force in terms of electrostatic force here can be written as K into charge of nucleus, which is Ze, into charge of electron, which is E, divided by square of the distance. So distance between them, we call it radius, right? So radius is square. And the centrifugal force, we can anytime write it as mv square by r, right? Now, one r can be cancelled. I can cancel this r from this square, and if I multiply E into E, in kze, I will get k z E square divided by r equals m into v square. So this is a formula we got by just equating centripetal and centrifugal force, right? And for mvr equals to nh by 2 pi, that means your angular momentum term, right? Bohr did not give derivation for this. He just used this conceptually. Later on, de Broglie explained this formula. De Broglie derived this formula, that how we have angular momentum is some n times of h by 2 pi. So using this formula of angular momentum and this, you can derive any of the formula. Suppose you have to calculate r, radius of orbit. So how you can calculate r? Just calculate m into v from here. M into v will be nh by 2 pi r, and substitute m into v here as nh by 2 pi r. You will get your r. If you want to calculate the velocity, so here substitute the value of mr or r. R will be nh by 2 pi mr. If you put here r as nh by 2 pi mr, you can calculate what? Velocity, right? And energy can be calculated from here. We get mv square, right? And you know that half of mv square is your kinetic energy, right? So half of this term, half of kze square by r is your kinetic energy. And in terms of charges, potential energy is given as minus of k q1 q2 by r. So for electron, the potential energy will be minus of k. Q1 means charge of nucleus Ze into charge of electron E upon r. If you add those two, you can calculate the total energy. So just from the angular momentum and centripetal centrifugal relation, from these two you can derive all those formulas anytime. But for questions, right, you need to remember all these formulas always, right? So after these Bohr parameters, now let's talk about one more thing, right, that Bohr explained in his model. So you can divide your Bohr model, students. You can divide your Bohr models in two parts. You can say like this: in one part, Bohr calculated the parameters of electron orbit, and in the other part, Bohr discussed about transition of electron or radiation by electron. Transition or radiation by electron. And he also explained the Rydberg equation. Which I will tell you later on. So first, let's discuss what is the meaning of radiation from an atom. And why electrons do radiation, right? So point is, if I consider atom according to Bohr, so this is my nucleus, and let's consider any of the two orbits of your atom, right? This is one orbit, right? And this is another orbit. It can be 1, 2, it can be 2, 3, it can be 1, 4, any two orbits, right? But out of these two orbits, you can see that one of the orbit is closer to nucleus and one of the orbit is away from the nucleus, right? So, the orbit which is closer to nucleus, I am calling it inner orbit and I am writing it as N1 orbit. And which is away from the nucleus, I am calling it outer orbit and this is your N2 orbit. Now, point is, if your electron anytime it is present in N1 orbit, inner orbit, right? So, your electron can jump from this inner orbit to outer orbit by absorbing energy, right? Automatically, electron will not jump from your lower orbit to higher orbit, right? It will jump only when it will absorb certain amount of energy, certain amount of quanta, right? So, when your electron goes from inner orbit to outer orbit, then it will do absorption. I am writing it here in short. When electron jumps from inner orbit to outer orbit, it will absorb energy. Why it will absorb energy? Because it will try to increase its energy, right? Overall, you need to understand that when your electron goes away from the nucleus, the total energy of electrons increases. And when your electron comes closer to nucleus, the total energy of electron decreases, right? So that's why to increase energy, electron will gain energy when it will go from inner orbit to outer orbit. On the other side, suppose if your electron is already present in the higher orbit and it is trying to jump into the inner orbit. So now I think you have understood, in this case, it will do radiation. Electron will radiate energy, right? So, when electron jumps from outer orbit to inner orbit, it will radiate energy. So basically that's how your electron does radiation, right? When it goes from lower orbit to higher orbit, it will absorb energy, and when it will come from higher orbit to lower orbit, then it will do radiate energy. And the point is, electrons do radiation in terms of electromagnetic wave. The absorption radiation by electron is done in terms of electromagnetic energy, in terms of electromagnetic wave. So you can say like this: when your electron goes from outer orbit to inner orbit, it will radiate energy, and it will radiate energy in the form of quanta, in the form of wave, right? Also, we can also calculate that how much energy is getting radiated using Bohr model. We can also calculate how much energy is getting radiated. Suppose that when your electron is in outer orbit, so here the energy of electron is E2, and when your electron is going into inner orbit, N1 orbit, so here the energy of electron is E1. So its energy is changing from E2 to E1. So what is the change in energy? E2 minus E1. So that much amount of energy will be radiated by the electron, right? So that's how you can calculate amount of radiated energy, right? The radiated energy by electron delta E can be calculated as energy of outer orbit minus energy of inner orbit. And we already know from Bohr model the formula of total energy of electron, right? Energy of electron when it is in outer orbit, E2, it is nothing but minus 13.6 Z square by N2 square, N2 orbit in electron volts, right? Minus, when it is in inner orbit, its energy will be minus 13.6 Z square by N1 square electron volt. So in N2 orbit, its energy is this. In N1 orbit, its energy is this. If you solve it, this minus minus will become plus, and this is minus only. And 13.6 z square can be taken common. So if I take that 13.6 z square common, I will get 1 by n1 square minus 1 by n2 square. And your energy will be in the units of electron volt. Your energy will be in the units of electron volt. So this is the amount of energy that gets radiated when your electron jumps from E2 orbit to E1, N2 orbit to N1, from energy E2 to E1, right? And later on, because we know that this energy is getting radiated in terms of electromagnetic wave, in terms of quanta, and energy of quanta can be written as hc by lambda, joule. This is electron volt. So if you equate these two, because this is energy of the wave and this is the radiated energy, and energy is radiated in terms of wave. So if you equate these two by equating the units, you get the equation, and that equation is nothing but your Rydberg equation. That equation, students, is nothing but your Rydberg equation. Rydberg equation. And Rydberg equation is nothing but 1 by lambda equals r z square 1 by n1 square minus 1 by n2 square. This is your Rydberg equation, and from this also you get so many questions in the NEET examination. So Bohr gave derivation of this Rydberg equation, right? Bohr gave derivation. Bohr derived this equation. How he derived this? You can also do it. It is in electron volt, right? So to convert electron volt into joules, you need to multiply with 1.6 into 10 to the power minus 19. So if I convert this radiated energy from electron volt to joule, it will be 13.6 z square into E into 1 by n1 square minus 1 by n2 square joules, right? Now, this energy, if it is getting radiated in terms of wave, so for that wave, the energy can also be written as what? hc by lambda. So when I equate these two, when I write that hc by lambda equals to 13.6 z square into E into 1 by n1 square minus 1 by n2 square, right? You can take that hc into right hand side, then 13.6 into E upon hc, that will be your constant. You can write it as Rydberg constant. So from here you get a formula that is 1 by lambda equals z square into constant into 1 by n1 square minus 1 by n2 square, and the same formula is known as Rydberg equation. So basically, what is the use of this Rydberg equation? You need to understand that. What Rydberg equation gives you? It gives you the parameter of wave which gets radiated during electronic transition. Students, please focus here. Point is, this is nucleus, this is your inner orbit, this is your outer orbit, right? So when your electron will jump from outer orbit to inner orbit, so we know that it is having some radiation. It is radiating some quanta, some wave. Now, whatever quanta, whatever wave it is radiating, if I want to calculate its parameter, I can start with Rydberg equation. Using Rydberg equation, first of all, I can calculate its wave number, 1 by lambda. From the wave number itself, I can calculate wavelength. From wavelength, I can calculate frequency. From frequency, I can calculate what? Time period. So, each and every parameter of wave can be calculated, right, using the Rydberg equation during the electronic transition. And from this formula also, you get so many questions in the exam, right? Now, in the same Rydberg equation or radiation by atom or hydrogen spectrum, right, we have a topic called spectral lines. I personally feel that spectral line is a very, very overrated topic. Why? It's a very easy thing, right? Very easy. What is spectral line? Students, each and every spectral line indicates a transition, a possible transition. Point is, you have your atom, you have your first orbit, you have your second orbit, you have your third orbit, you have your fourth orbit, and so on up to infinity. So if I go orbit by orbit, if I consider each and every orbit one by one, so I can say like this: for the first orbit, if electron jumps from 2, 3, 4, 5, infinity, every time I will have radiation. So for the first orbit, what are the possible transitions from which electron can do radiation? That can be indicated by drawing these spectral lines, right? Like for the first orbit, electron will do radiation when it will jump from 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, 7 to 1, infinity to 1. Now here, whatever lines you are drawing, these lines are called what? Spectral line. So spectral line indicates a transition. If you have drawn 10 lines here, so that indicates 10 possible transitions. And for each transition, there will be radiation of one quanta, right? So you can also say like this, that spectral lines, they indicate quantas. How many quantas are getting radiated or how many transitions we are having, right? And this can be done for all the orbits, like for n equals to 2, right? For second orbit, electron will do radiation when it will jump from 3 to 2, 4 to 2, 5 to 2, 6 to 2, 7 to 2, infinity to 2. Similarly, for n equals to 3, electron will do radiation when it will jump from 4 to 3, 5 to 3, 6 to 3, 7 to 3, infinity to 3, right? For n equals to 4, electron will do radiation when it will jump from 5 to 4, 6 to 4, 7 to 4, infinity to 4. And what we have done for each orbit, for each transition, for each spectral line, for each set of spectral line, we have given them names, right? All the possible transitions of first orbit, they are called Lyman. All the possible transitions of second orbit, they are called Balmer. For third orbit, Paschen. Fourth, Brackett. Fifth, Pfund. Sixth, Humphrey. Right? So you need to understand exactly what is the meaning of these Lyman, Balmer, Paschen, Brackett, Pfund, Humphrey are. Right? These terms indicates your possible transition, right? So you can also say like this, when I say Paschen, so Paschen means the n1 value is always 3, n2 can vary. When I say Lyman, so n1 value is fixed 1, but n2 can vary, right? Not only this, in Lyman transition, whatever waves, whatever quantas are radiated, they lie in the ultraviolet region of electromagnetic spectrum. For Balmer series, whatever transitions we have, in those, the quantas are radiated from the visible region, right? And for rest, Paschen, Brackett, Pfund, we have infrared and we call it as near infra, far infra and far infra. So this point you need to memorize, you need to remember that in case of Lyman transition, the quantas radiated, they are from UV region. For Balmer, visible. And for rest, infrared, Paschen, Brackett, Pfund. Right? And from this you get questions again by combining these spectral lines with your Rydberg equation. They will ask questions. What type of questions? That suppose if I talk about Balmer series. So in Balmer series they can ask like this. What is the maximum wavelength that can be radiated? Or what is the minimum wavelength that can be radiated in the Balmer series? So you need to understand a little bit here. When I say maximum wavelength radiated, so maximum wavelength means minimum energy is radiated, because energy wavelength, they are inversely proportional to each other. And in Balmer series, minimum energy will be radiated when your electron will jump from 2 to 1. Similarly, if I say that in Balmer series, when I will be having the minimum wavelength, so minimum wavelength I can get when maximum energy is radiated, and maximum energy is radiated when your electron jumps from infinity to 2. Okay, I was talking about Balmer series, not Lyman, right? So in Lyman series, let me correct it. It should be 3 to 2, right? Because in Balmer series, the n1 value is always 2. So in Balmer series, minimum energy is radiated when your electron jumps from 3 to 2. And maximum energy released when your electron jumps from infinity to 2. Similarly, you can do for the rest of the series. In case of Lyman series, maximum wavelength or minimum energy is radiated when your electron jumps from 2 to 1. Right? In the same Lyman series, minimum wavelength or maximum energy can be radiated when your electron jumps from infinity to 1. right? So from these points you will be getting questions in your examination, right? So let's see few questions from these Bohr models, right? And I hope that now you have understood in Bohr model we have two parts. You can classify Bohr model into two parts. One part parameters of orbit electron and one part radiation, Rydberg equation and spectral lines. So let's do few questions from this. The first question is the ratio of the wavelength of the light absorbed by hydrogen atom when it undergoes transition from 2 to 3. So lower to higher orbit, in this case absorption will happen, and 4 to 6. And we have to find the ratio. So one by one you can find the wavelength. Like if you talk about transition from 2 to 3, right? So for 2 to 3, let me call it lambda 1 and let me apply Rydberg equation here. 1 by lambda 1 will be equals to R Z square 1 by n1 square, right? So 1 by n1 square is what? n1 means lower orbit. n1 means lower orbit. So 1 by 2 square is 4 minus 1 by 3 square is 9. So from here I will get the wavelength of this transition. And for 4 to 6, right, I call it lambda 2 and I can get it as RZ square 1 by n1 square. So n1 again lower orbit, so 4 square 16 minus 6 square 36. So I have to find lambda 1 upon lambda 2. I have to find lambda 1 upon lambda 2. And in both the cases we have hydrogen atom, so Z square will be 1 in both the case, right? So in the first case if I calculate 1 by lambda 1, it will be R, Z square is 1, LCM of 9 and 4 is 36 and it will be 4 9s are 36, 9 minus 4, 5. So overall I can say that here, from here if I calculate lambda 1, so lambda 1 will be 36 upon 5R. Similarly, if I calculate lambda 2 from this, right, so 1 by lambda 2 will be R, Z square is 1 and 16 and 36, if you write it down, let it be 16 into 36. So in the numerator it will be 36 minus 16 which is 20, correct? So from here lambda 2 you can get as 16 into 36. Do not calculate in between. Don't start multiplying 16 and 36. You can do the calculation at the end. Final calculation always multiplication division should be done at the end. So this is your lambda 2. Now what you have to do? You have to just find the ratios of wavelength of these two, lambda 1, lambda 2. So lambda 1 upon lambda 2 will be equals to, lambda 1 is 36 upon 5R upon lambda 2 is 20R in the numerator, 16 into 36. So many things will be cancelled here, right? R will be cancelled, this 36 will be cancelled, from 5 it will be cancelled 4 times, from 4 it will be cancelled 4 times. So it is simply coming 1 by 4. It is coming simply 1 by 4. 1 by 4. So answer in this case should be A. But we are not interested in the answer only. I hope that now you should do these types of questions. So for two radiations here, we have to get the wavelength and we have to find the ratio of wavelengths. So definitely in this case, your answer will be A. That means 1 by 4. And this question is very recent. We got it in NEET 2025 examination. So now I hope these types of questions you can do easily, right? Let's not stop here. Let's do more questions from Bohr model. Again, energy and radius of first Bohr orbit of helium plus and lithium 2 plus. So this is a question now from the other topic, from the parameter part, right? And here what you have to do, you have to calculate both energy and radius of both helium plus and lithium 2 plus. So one by one you can solve. Like first you can take helium plus ion, and in helium plus ion you know that its atomic number is 2, right? And we have to take first Bohr orbit, means we have to take n equals to 1. So z equals to 2, n equals to 1, and we have to calculate energy and radius. So first of all, if I calculate energy of this helium plus, right, for the first orbit, it will be minus 13.6 into z square means 2 square upon n square means 1 square. electron volt. It will be minus 13.6 into 4 electron volt. If you want your answer in joules, so electron volt can be converted into joule just by multiplying by 1.6 into 10 power minus 19. This is also the value of charge of electron. Now similarly, if I calculate the radius of helium plus for the first orbit, the formula was 0.529 into n square. N square will be 1 square here upon z, which is 2, right? And it will be in angstrom. If you want this in meter, SI unit, you know that 1 angstrom is 10 to the power minus 10 meter. So it will be 0.529 into upon 2 into 10 power minus 10 meter. So I calculated for helium. You can calculate for lithium also in the same way, right? For lithium, 2 plus ion. For lithium, first of all, atomic number is 3 and orbit we have to take again first, right? So here if you calculate energy, it will be minus 13.6 into z square, 3 square, which is 9 upon 1 electron volt. Again, you can convert that into joule by multiplying with 1.6 into 10 to the power minus 19. And if I calculate the radius here, so radius for this lithium 2 plus first orbit will be 0.529 into n square, means 1 square, by z, which is 3 angstrom. If you want in meter, you can multiply by 10 to the power minus 10. So from the parameter part, you will always get direct formula based question. You remember the formula, energy, radius, angular momentum, velocity. You can directly solve the question just by applying the formula. So if you do the calculations, energy of lithium, you will get minus 19.6 10 to the power minus 18. Radius of lithium, you will get 17.6 picometer. Energy of helium plus, you get minus 8.7 10 power minus 18 joules. And radius of helium plus, you will get 26.4 picometers. So the next question we have is statement type problem. Statement 1 is do it first by your own, right? Pause the video, calculate it. Later on you can match the answer with me. So question is, statement 1 is, the Balmer spectral line of hydrogen atom with lowest energy is located at 5 by 36 RH, means RH is your Rydberg constant. So first of all, you know what is the meaning of Balmer spectral line. Balmer means when you are having transition from nth orbit to 2 orbit, right? From anywhere, from any orbit, if your electron is jumping and finally it is reaching in the second orbit, right? N1 is 2, then you call it as Balmer series. And hydrogen atom means what? Atomic number is 1 and lowest energy. So in Balmer series, lowest energy will be radiated when you have a transition from the third orbit to the second orbit. Third orbit to the second orbit, and the same transition in which you are having lowest energy transmission, right? In the same case, you will be having maximum wavelength radiated, right? So we got our transition, it is 3 to 2. We have atomic number and we have to calculate what? We have to calculate the wave number here. The wave number here, 5 by 36 R. So let's check it out. Let's calculate the wave number. 1 by lambda is equals to R, H, Rydberg constant, into Z square. Z square will be 1, so we can skip that. 1 by N1 square. So N1 is 2 here, so 2 square will be 4 minus N2 square. So N2 is 3, so 3 square is 9. If you calculate it, then your wave number 1 by lambda will be RH. LCM of 9 and 4 is 36 and 9 minus 4 is 5. So definitely our wave number is coming RH into 5 by 36, which is given in the statement 5 by 36 into RH. So definitely here statement 1 is absolutely correct. Now if you look into statement 2, so when the temperature of black body, so it's a question from black body radiation, when the temperature of black body increases, the maxima of the curve, intensity of wavelength shift to shorter wavelength. So we have seen that, right, in the graphical part. Remember, in the black body radiation, right, on the x-axis if you plot wavelength, on the y-axis if you plot intensity, right? So at lower temperature, if your graph is like this, so at higher temperature your graph will go like this. So we know that the maxima point shift on the left hand side, on the left hand side. And that's why we said in black body radiation that when your temperature is increased, right, the radiated wavelength decreases. Temperature and radiated wavelength was inversely proportional in that case. So definitely they are also saying that when the temperature of black body increases, the maxima of the curve intensity of wavelength shift to shorter wavelength. Shorter wavelength means left hand side. So this is again absolutely correct according to the curve of black body radiation. So statement 2 is also correct. So what we can see here, that both statement 1, statement 2 are correct, and so the answer will be none other than C. Yeah, answer is C. And this simple question of statement based, basically you can say that this question was a mixed question of Rydberg equation and black body radiation, but we got it in NEET 2024 examination, right? Now moving further, let's do more question from this Bohr model, Rydberg equation. Now the next question is, the energy of an electron in the ground state, that means first orbit, for helium plus ion is minus x joule. Then what will be the energy for electron in the second orbit, right, in the second orbit for barium 3 plus ion. So beryllium 3 plus ion, not barium, beryllium 3 plus ion. So it's a direct question, again formula based from the parameter part, right? For helium plus, if I apply the formula, I can say that total energy is minus 13.6 Z square by N square electron volt, right? So for helium, the energy is given how much? X joule. So I just substituted the value, energy is minus x joule. This equals to minus 13.6 Z. So for helium, atomic number is 2. So Z square will be 4. 2 square 4. Upon N square, we have to take the first orbit, that means 1 square is 1 electron volt. See, from this given information, what you can do, you can make a relation between your electron volt and joule, right? Minus minus is cancelled out. Now you can say what? You can say that x joule is equivalent to 13.6 into 4 electron volt. Just remember this relation, because this we will need in the next part. Now for beryllium 3 plus, if I calculate the total energy using the same formula, so now it is minus 13.6 Z square. So for beryllium, the atomic number is 4, and we have to take the second orbit, right? So here Z square will be 4 square means 16 upon N square will be 2 square 4 electron volt. Now please listen, 13.6 electron volt, I can keep it as x by 4 joule from this relation, x by 4 joule, right? So minus 13.6 electron volt, I will write it as x by 4 joule, and what is remaining here? 16 by 4, right? So 4 into 4 is 16, and in numerator also we have 16, 16 will be cancelled. So this is also coming same, this is also coming minus x joule. So in this case also the answer is C. So in this question, the formula we use is just for total energy, but the main thing is, from the given value of energy of helium plus ion, we just calculated a expression, a relation between the electron volt and joule, and I use that in the next part while calculating energy of beryllium. So in this case, answer should be C, and of course it is C, and this question we got in NEET 2024 examination again, right? Now let's look into one more problem from again Bohr model, right? And this question is also from the parameter part, right? If radius of second Bohr orbit is 105.8 picometer, so for the second orbit means N is 2, and your ion is helium whose atomic number is again 2, and its radius is given. So what is the radius of third Bohr orbit of lithium ion? So it's a same type of question, the previous one. The only difference is in the previous question we had to discuss in terms of energy, and here we have to discuss in terms of radius, right? But same way we can do the calculation. So for helium, the formula of radius will be 0.529 into N square by Z angstrom. Now the radius is given in picometer, how much? 105.8 picometer. equals to 0.529 into n square. So in this case n is 2, so 2 square is 4 divided by Z. So for helium Z is 2. So this is cancelled 2 times angstrom. Now from this relation what I will get a equation between angstrom and picometer. I will get a relation between the unit angstrom and picometer, and that I will use in the next part while calculating radius of lithium. So from here I can write it down like this: 105.8 picometer, right? Take this 2 into LHS, so upon 2 equals to 0.529 angstrom, right? Just remember this relation. Now calculate radius of lithium ion, right? So for lithium ion the atomic number is 3 and we have to calculate for third Bohr orbit, means n is also 3 here. So now if I calculate radius of lithium, it will be 0.529 into n square. So n is 3 here, so square of 3 is 9 divided by Z. Z is 3. So this is cancelled 3 times and it is in angstrom, right? So this will be 0.529 into 3 angstrom. Now what I can do, I can substitute 0.529 angstrom as 105.8 upon 2 picometer, right? So it will come out 105.8 upon 2 into 3 picometer. If you calculate this, you will definitely get your answer. We can cancel it out by 2 5s are 10, 2 2s are 4, 0.29s are 18. And if you multiply with 3, 9 3s are 27, 2 3s are 6, 2 8, 5 3s are 15. So it is coming roughly 158.7 picometer, 158.7 picometer. Just like that energy problem, here also you can notice that the radius of helium ion is given, right, just to obtain a relation between angstrom and picometer. Using that, the calculation becomes easier. You can do very fast calculation by substituting angstrom in picometers in these terms, right? So finally here the answer will be B, and this question again from Bohr model we got in the NEET 2022 examination. So many questions we get in our NEET exam from this Bohr model, and from both the parts, from the parameter part also and from the radiation, Rydberg equation and spectral line parts, right? Now finally a direct question we have from the spectral lines. Can you all answer this in the chat box quickly, in the comment box quickly? Which of the following series of transitions in the spectrum of hydrogen atom falls in visible region? So basically we have to answer that in which series the radiated waves, they lie in the visible range of electromagnetic spectrum, right? And we have seen that, right? In case of Lyman, it is ultraviolet. In case of Balmer, it is visible, and in case of Paschen bracket P fund, it is infrared, right? Near, far. So they are asking for visible. So definitely in this case answer will be Balmer series. In Balmer series we get the visible region quantas, visible region electromagnetic wave, and this easier question we got in the NEET 2019 examination. So now I think you have understood very well what we have to discuss in Bohr model, and you practiced questions from Bohr model, right? But I hope you know that Bohr model is not the end of this chapter, right? After Bohr model we have to discuss about the quantum model, right? But before we move further in quantum model, we have to see the background of quantum model. You can say that why we started framing quantum model, using quantum model, and why Bohr model failed, right? So in order to understand why your Bohr model failed, you need to understand few points like dual nature, Heisenberg, uncertainty principles and all. And from those topics also, you definitely get questions in the examination, right? So what do we mean by dual nature? Students, what do we mean by dual nature? See, anything or everything that you see in your surrounding, right, that you can define as energy. That you can define as what? Energy. And we can classify energies into two categories, either wave or particle. Either wave or particle. And those waves and particles, they have difference in properties, like particles If you talk about particles, they have mass, they occupy space, volume, right? They have collision. But if you talk about wave, they don't have mass, they are massless, they don't occupy volume, they don't occupy space, and they do not have collision. Instead of collision, they have interference and diffractions, right? So in the properties part, wave and particles, they have difference. But overall, wave is also energy, particles are also energy. Now, what if something has both the nature? If there is something which has properties of wave as well as particle, right, then we say that that particular thing has dual nature. Means it can behave as both wave and particle. And you know that light is one of them. Light is one of them. Light has dual nature, right? Light has behavior of wave and behavior of particle. But do you know that apart from light, even your electron has dual nature? Even your electron has dual nature. Electron, earlier we used to think that electron is a particle, right? Even in the cathode experiment, you measured mass of electron and all, right? So earlier we used to think that electron is a particle. But the concept of dual nature, right, suggested that even your electron has wave nature, right? Electron has wave nature. So overall, what you can interpret, that just like your light, which has dual nature, even your electron has dual nature. Electron has dual nature. And this is one of the reasons why your Bohr model failed, right? In Bohr model, Bohr considered electron just as a particle. Bohr ignored the wave nature of electron, right? But in the further quantum model, right, we considered both. For electron, we considered wave nature as well as particle nature. So point is, when sub-energy is there, which has both wave and particle behavior, then we say that it has dual nature. And de Broglie, right, he derived a very beautiful relation of dual nature. What he said, that if something is there, some energy is there, and it is wave, right? So in terms of wave, its energy, we can write it as hc by lambda, right? If some energy is there, it is behaving as a particle. So in terms of particle, we can write its energy as E equals to mc square. So if some energy is there which has both wave and particle nature, and I calculate energy in terms of wave, in terms of particle, so I am calculating energy of the same thing. So both the energy should be equal. If something has dual nature, then whether you calculate your energy in terms of wave or assuming it to be a particle, both energy should be equal because you are calculating for the same thing. Now when you equate these two, right, one of the c will cancel the square, you will get a relation that lambda equals to h by mc. Mc is nothing but momentum, right? So from here, de Broglie concluded that wavelength is equals to h upon m into c is nothing but momentum. Wavelength is inversely proportional to the momentum, right? And here he got a relation between a parameter of wave, which is wavelength, and parameter of a particle, which is momentum. And this equation, lambda equals to h by momentum, we call it de Broglie's equation or equation of dual nature. Also, if it is an electromagnetic wave, right? So in terms of electromagnetic wave, you write it as lambda equals to h by mc, where c is your speed of light. But if you apply the same formula for your daily life objects, right? So like for a car, for a bus, for a cricket ball, right, their speeds are not equals to speed of light. So in those cases, we use their speed, right? Their speed of car, speed of ball, to calculate their wavelength, right? So in that case, the wavelength can be written as Planck's constant upon m into velocity. And this is what you call as de Broglie's equation. Not only this, instead of writing lambda equals to h by momentum or h by mv, you can also write this formula in terms of kinetic energy or stopping potential, right? Momentum can be also written as square root of 2 into mass into kinetic energy, right? So de Broglie's equation can also have one more form, which is h by under root of 2 into m into kinetic energy, mass of particle into kinetic energy of particle. So all these equations are same, they are de Broglie's equation. They are the equation of dual nature. And from this, you get direct question, right? Direct questions. Direct means they will give you wavelength, they will ask for velocity or momentum or vice versa, right? Now, why we are talking about dual nature here? Because dual nature is a drawback for Bohr model. Dual nature is a drawback for Bohr model. And I have already explained that to you in terms of electron, right? After the concept of dual nature, we got to know that electron can have dual nature, which was ignored in the Bohr model part, right? Now, apart from dual nature, there is one more point which comes under, you can say, failure of Bohr model, and that is Heisenberg uncertainty principle, right? It's a very famous principle, right? If you study this one time, you will never forget it for your whole life. Never, right? What it says that it is impossible to determine the exact position and momentum of a particle simultaneously. Means if there is a moving object, right? So that object will have some velocity, it will have certain momentum, right? And it will continuously change its position if it is moving, right? So for a moving object, you cannot calculate or determine the exact position in 3D space and its exact momentum. Although in your physics chapters like linear motion, right, motion in a straight line, you do calculate, right, displacement, velocity, initial velocity, right, acceleration, everything you calculate. But according to this statement, there also you can't calculate, right, exact position or exact displacement. But point is, in physics, you deal with macro objects, right? And for macro objects, this theory can be neglected, can be ignored. Because the error that you get in your daily life for the macro objects, it is very less. So you can ignore that. But when we determine the position momentum of particles on micro level means atom, molecule, electron, proton, neutron, nucleus, right? So on micro level, you cannot ignore this theory. You cannot ignore Heisenberg uncertainty principle. So what you have to do there, you have to assume that we always have some error in position and momentum. So when we calculate for any electron, let's say, for any electron, if I calculate position and momentum, so I will always get some error. And if the error in position is delta x and error in momentum is delta p, so Heisenberg said that multiplication of these two error or these two uncertainty will be always greater than equals to h by 4 pi. Will be always greater than equals to h by 4 pi. So h by 4 pi is your minimum error, right? Okay, when you do some numerical questions, right? So questions will be there in which delta x will be given, delta p you have to calculate. So for numericals, you can put it equal sign. You can write delta x into delta p equals to h by 4 pi. Matlab means there you can consider the minimum possible error, h by 4 pi, right? Also, instead of momentum, you can write it here m into delta v, So then it will be delta x times delta p means m delta v, right, greater than equals to h by 4 pi. And again from this formula, you get a direct question in the exam. So overall, what I can say that dual nature and Heisenberg uncertainty principle, these two are the drawbacks of Bohr model. So finally, if I summarize what are the causes of failure of Bohr model, I can write 2 or 3 points at least here. First point will be Bohr ignored wave nature of electron, and this point we have according to dual nature. Second point, we can directly say that Bohr model is 100% wrong according to Heisenberg uncertainty principle. Okay, why it is wrong according to Heisenberg uncertainty principle? Because in Bohr model, right, he calculated exact position in terms of radius, right, and momentum, velocity. So those calculations, definitely they will have error. Those calculations are not accurate. So that's why according to Heisenberg principle, all those calculations of Bohr, like they will have error. They will have flaw in it, right? So after these two, one more point I can write in the failure of Bohr model, and it is, this model is applicable, it is applicable only for one electron species. Bohr model, still you can apply, right? Still you apply Bohr model, right? But wherever there is a species, atom, ion which has only one electron in it, so species which has only one electron in it, for them you can apply Bohr model, right? If your species, atom, ion has more than one electron, then you cannot use Bohr model. And overall, always remember in this chapter, whenever you are applying some concept, right? So if it is a one electron species, you can apply Bohr model, especially for the energy comparison part, For one electron species, you can apply Bohr model, and when your species has more than one electron, then you need to use quantum model. For multi-electron system, you need to use what? Quantum model. So now students, let's see some questions from these two topics, like Heisenberg uncertainty principle and de Broglie's equation, right? So point is, we have a question here, you can pause it and you can do it by your own, and later on again you can match the answer. Question is, if I have a 0.66 kilograms ball that is moving with a speed of 100 meter per second, the associated wavelength will be. So in this question, we have a ball, right? And it is moving at certain speed 100 meter per second. Its mass is given, and we have to just calculate the wavelength associated. So point is, for any particle which has mass, if you want to calculate wavelength, only formula that you will be using is de Broglie's equation, right? So just now I have told you, de Broglie's equation is lambda is equals to h upon momentum m into v. So from this we can calculate the associated wavelength of that ball, right? H is 6.626 into 10 to the power minus 34 divided by mass of this ball is given 0.66 kg, right, into velocity or speed is given 100 meter per second, right? So if you calculate roughly, right, from 100, if I take 10 and multiply this, so 6.6 upon 6.6, round off it is 1, right? And 10 to the power minus 34 upon 10 is nearly 10 to the power minus 35. So near about, the wavelength associated will be 10 to the power minus 35. 10 to the power minus 35. So answer should be C. Answer should be C, that is 10 to the power minus 35 meter. And one more thing you can notice here, that this particular value of wavelength is very small, right? If you talk about electromagnetic waves, so for electromagnetic waves, the wavelengths are in the order of nanometer, 10 to the power minus 9, 10 to the power minus 10. So as compared to the wavelength of EM radiations, right, these values are too much small. That's why we ignore in macro objects, especially the dual nature part. Now, the next question is from Heisenberg uncertainty principle, and it is, if uncertainty in position and momentum are equal, okay, so we know that we have error in position and also we have error in momentum when we measure them. Now they are saying that if the uncertainty or error of both are equal, then uncertainty in the velocity we have to calculate. So just apply that Heisenberg equation, delta x into delta p is equals to h by 4 pi. For calculation you can use equal sign here, right? Now if delta x, delta p both are equal, so I can write it as delta x into delta x equals to h by 4 pi, or I can write it as delta p into delta p as h by 4 pi. So I can substitute this delta x, error in position, as delta p because both are equal. In this question, error in position and momentum are equal. So I will substitute this delta x with delta p. So it will become delta p whole square is equals to h by 4 pi, right? So from here, delta p will be square root of h upon 4 pi. And you know that delta p or error in momentum can be written as m into delta v, mass into error in velocity, and this should be equals to h upon 4 pi square root. Now from here, if I calculate the delta V, that means uncertainty or error in velocity, so that will be 1 upon m into under root of h upon 4 pi. 1 upon m under root of h upon 4 pi. Okay, 4 you can take outside, so square root of 4 will be 2. So I can rewrite it as 1 upon 2m, right, into under root of h by pi. So the answer will be 1 by 2m into under root of h by pi. That means again C is your answer. Yeah, 1 by 2m under root of h by pi. And this question we got in the NEET 2011 examination, 2011 NEET, right? They asked this easy question from the Heisenberg uncertainty principle. So now I hope you have understood very well that what we have to study, what we have to revise in the Bohr model, and also why that Bohr model failed, right? So after Bohr model, let's go into the final part of this chapter, that is quantum model, right? And in quantum model, first of all, we need to understand what is wave function. What is wave function? So wave function, it is denoted by psi, and it is nothing but a mathematical description, of your electron in terms of orbital. So psi or wave function is nothing, just a mathematical equation, right? See, in your mathematics, you have so many equations, but every equation you cannot relate in your daily life, right? Every equation cannot have physical significance. Same like this psi is a mathematical equation, right? Mathematical function, wave function, right? It has some values, right? But it does not have any physical significance. You cannot directly interpret anything from that wave function. It is just an equation, right? So always remember that psi, which is a mathematical function, which we call wave function, right? It gives you information regarding your electron orbital, but directly psi does not have any physical significance. Does not have any physical significance. If something does not have a physical significance, means you cannot explain that by taking some real life example. If a mathematical equation is there, right, which you can explain in your daily life by some phenomena, that means it has physical significance. But if you can't do that, if you cannot explain a mathematical equation by some real life event, right, by some concept, by some atom molecule, that means it does not have any physical significance. So psi is a wave function of orbital. It is completely mathematical. It gives you information regarding your orbital, but it does not have any direct physical significance, right? And why we talked about wave function here, right? Why we talked about wave function here? Because wave function is nothing but your atomic orbital, right? These mathematical equation gives you information about orbital. Okay, I hope that you all understands what is the meaning of orbital, right? Again, if I go in a sequence, I can say like this: in Thomson model we got electron, in Rutherford model we got nucleus, in Bohr model we got orbit, and now in the quantum model we got orbital. What is orbital? Orbital is the 3D space in which you can predict where your electron is present or not, right? Or whether there is a probability of finding electron or not. So the 3D space in which we have a probability of finding electron, that space we call it as orbital, right? And for every orbital, for each and every orbital, you will have a wave function, you will have a mathematical equation, right? Now, these wave functions, right, you can observe in the Schrodinger equation, right? Because in quantum model, what we have done, we have applied the Schrodinger equation for atom, for electron, right? And then we have formed or created the quantum model. So I hope Schrodinger equation is something like this: dou square psi upon dou x square plus dou square psi upon dou y square plus dou square psi upon dou z square plus 8 pi square m by h square into E minus V into psi equals to 0. So this is your Schrodinger equation in which this psi is nothing but your wave function. This psi is your wave function. It has some mathematical expression, right? X, Y, Z, they are your X, Y, Z Cartesian coordinates, and this is called partial differentiation. This is like a partial differentiation. And if you notice this term in Schrodinger equation, so 8 pi h, they are constant. M, if you are applying it for electron, then it is mass of electron. Here E is your total energy. E is your total energy and V is your potential energy. And again psi is your wave function. So you can note down this Schrodinger equation, but you don't have to remember it. You will never get a direct question from this Schrodinger equation, and no one will ask this to you, right? And even no one will ask the derivation of Schrodinger equation from you. Why we are talking about Schrodinger equation? Because by solving this Schrodinger equation, by applying this Schrodinger equation for electron, right, we obtained quantum numbers. We obtained quantum numbers. Now, there are total 4 quantum numbers that you will study: principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. But out of those 4 quantum numbers, always remember that only principal quantum number, azimuthal quantum number and magnetic quantum numbers are obtained by Schrodinger equation. A spin quantum number, we have not obtained that from the Schrodinger equation. From Schrodinger, we get only 3 quantum numbers, right? They are principal, azimuthal and magnetic. Now, from the quantum numbers, from this part, you get questions in your exam, right? So first you need to understand what is the exact meaning of these quantum numbers, right? So the very first quantum number is principal quantum number. Principal quantum number. The second quantum number you have is azimuthal quantum number, right? The third one is magnetic quantum number. Magnetic quantum number. And the fourth one is spin quantum number. Spin quantum number. Principal quantum number, it is denoted by small n. Azimuthal quantum number is denoted by small l. Magnetic quantum number is denoted by small m, and spin quantum number by small s. So these are the representations of your different quantum numbers. Now the first point is, what is the meaning of these quantum numbers? What we can interpret from these quantum numbers? Students, you know very well about your sequence and series, right? Like when you say prime numbers. So in prime numbers, you have certain set of numbers, right? 1, 3, 5, 11, 7, so on, right? When you say even number, when you say odd number, when you say integer, right? So all these things are set of certain numbers. So same thing, same concept is there for these quantum numbers. All of these quantum numbers, initially, forget about what is the application of these in your atoms, how they are related with your atoms, right? First of all, try to understand this just like that they are set of certain numbers. They are set of certain numbers, right? Principal quantum number, it is 1, 2, 3, 4, so on up to infinity. So 1, 2, 3, 4, 5, 6, 7, 8 up to infinity, these are the numbers of principal quantum number, right? And they are nothing, they are taken from Bohr model. They have been taken from Bohr model, right? In Bohr model, right, you call orbit number, right? Orbit numbers are 1, 2, 3, 4, 5, 6, 7, 8. So the same orbit number in quantum number, we have changed its name, right? And now the orbit number is called as principal quantum number, right? Similarly, if you talk about azimuthal quantum number, so azimuthal quantum number starts from 0 and again it is 1, 2, 3 and so on. So 0, 1, 2, 3, 4, these types of values we have for the azimuthal quantum number, right? For magnetic quantum number, we have values like 0, but here we have both plus and minus values, right? In principal and azimuthal, we don't have negative values, only positive. But for magnetic quantum number, the values, possible values can be 0, plus 1, minus 1, plus 2, minus 2, plus 3, minus 3 and so on. And the most easiest one is spin quantum number. For spin quantum number, we have only 2 possible values, plus half or minus half, plus half or minus half. So I have not told you that what is the use of these quantum numbers in your atom. Currently I have told you that these are the set of numbers. Principal quantum number is from 1 to infinity. Azimuthal quantum number is from 0 to infinity, right? Magnetic quantum number is from 0, plus 1, minus 1, plus 2, minus 2, plus infinity, minus infinity. Spin quantum number is only plus minus 1 by 2, right? But point is, these values are not independent. These values are not independent. They have relation in between them. Like your azimuthal quantum number depends on principal quantum number. Similarly, magnetic quantum number depends on both azimuthal and principal quantum number. And spin quantum number is independent of these two because spin quantum number tells you just about the spin of electron. If your electron is having a clockwise spin, then it is plus half. If it is anti-clockwise, then minus half, right? So first, now let's see how they are dependent on each other. So first of all, the principal quantum number, it's an independent parameter, right? We have directly taken it from Bohr model. But if you talk about your azimuthal quantum number, right? So azimuthal quantum number or its value is always from 0 to n minus 1, or you can say that this is the range of azimuthal quantum number. Means what? If you take your first orbit, if you take principal quantum number's value as 1, so for n equals to 1, the value of L will be only 0. If you take n equals to 2, the possible values of L will be from 0 to 2 minus 1, means 0 and 1. If you take n equals to 3, then the possible values of L will be 0, 1, 2. If you take n equals to 4, then the possible values of L will be 0, 1, 2, 3. So point is, the range of azimuthal quantum number depends on your principal quantum number, right? The azimuthal quantum number's value will be always smaller than your principal quantum number. If your principal quantum number is 4, then it will be up to 3. If your principal quantum number is 2, then will be up to 1. Right? From these also you get direct questions in your examination, and we call it as a condition on quantum number, right? Okay. Apart from azimuthal quantum number, if you talk about the magnetic quantum number, right? So magnetic quantum number, it also depends. The values of magnetic quantum number, it directly depends on the azimuthal quantum number value, right? For any L value, right, the values of magnetic quantum number lies between minus L to plus L. So that's the range of your magnetic quantum number. For example, if you take azimuthal quantum number 0, so for this magnetic quantum number will be minus 0 to plus 0, means 0 only, right? If you take L equals to 1, if your azimuthal quantum number value is 1, right, then the range of magnetic quantum number will be minus 1 to plus 1, means minus 1, 0, plus 1. If you take your azimuthal quantum number value as 2, right, then the values of magnetic quantum number will be minus 2, minus 1, 0, plus 1 and plus 2, and so on. If you take L equals to 3, then the possible values of magnetic quantum number will be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So kind of we have restrictions in the values, right? We have restrictions in the values of magnetic quantum number because it is always dependent on azimuthal value, and we have limited values of azimuthal quantum number because it is dependent on principal quantum number values, right? And from these dependency you get questions, right? When we will practice question, so there you will see, right, we have condition based questions on this, right? And of course spin quantum number, it is independent, it has only two value, plus half, minus half. Plus half means when your electron has clockwise spin, and minus half means when your electron has anti-clockwise spin. So now we are done with what is quantum number and what are the possible values of your quantum numbers. Now let us relate these quantum numbers with your atom, with our atom, right, one by one. So first of all, if you talk about the principal quantum number, students, principal quantum number. So you can understand like this, the principal quantum number values, they represents the orbit, right? When your principal quantum number value is 1, means it is your first orbit. If it is 2, means second orbit. 3 means third orbit. So each value of principal quantum number indicates an orbit, shell, right? On the other hand, when you talk about azimuthal quantum number, so each and every value of azimuthal quantum number represents a subshell. A subshell. Subshell means it is a part of your shell. It is a part of your orbit, right? So you have orbit, and inside orbit you have suborbits or subshells, right? And each value of azimuthal quantum number indicates one subshell, right? When I say L0 means it is a subshell. When I say L1, it is a subshell. When I say 0, 1, 2, so that means we have three subshells, 1, 0, 1, 1 and 1, 2. And these subshells, they have alphabetical notations also. If you remember, the orbit, right, in terms of number it is 1, 2, 3. In terms of alphabet we call it KLMN, right? N1 is K, N2 is L, N3 is M, and so on. Similarly, each subshell, right, it can be denoted by number 0, 1, 2, 3, but it can also be represented by alphabets, right? Like whenever L is 0, so it is your S subshell. L0 means S subshell. Whenever it is 1, it is your P subshell. 2 means D subshell. 3 means F subshell, right? So whenever you have L values, so if the value of L azimuthal quantum number, it is 0, means it is your S subshell. If the value of L is 1, that means it is your P subshell. If the value of L is 2, that means it is your D subshell. 3 means F subshell. So each azimuthal quantum number's value indicates an subshell, a subshell, right? So principal quantum number represents orbit and azimuthal quantum number represents what? Subshell. Now, talking about magnetic quantum number, each magnetic quantum number indicates or represents an orbital. Each magnetic quantum number value indicates, signifies an orbital, right? So when you say m equals to 0, means it is indicating one orbital. There will be an orbital whose m value is 0. When you say that we have three values of magnetic quantum number, -1, 0, +1, means we have three orbitals, right? One of the orbital has m value as -1, one has m0, one has m +1. So each value of a magnetic quantum number indicates, represents an orbital. So that is the relation of quantum numbers we have in the atom. Principal quantum number, orbit; azimuthal quantum number, subshell; magnetic quantum number, orbital, right? And you can understand in a simple way like this: inside orbit you have subshell, inside subshell you have orbital, right? So now you understood that how they are related, how these quantum numbers are related with orbit, orbital and subshells. And we have already seen possible values of quantum numbers, right? Possible values of quantum numbers, correct? How they are dependent on each other. So now let us see a very, very interesting topic, and from this also you get direct questions in your examination, right? Sometimes they will ask to count, to calculate number of orbital or number of electron in a given shell or subshell. Either in shell they will ask or in subshell they will ask. So suppose if they ask that what is the number of orbital in n equals to 4? Simply, what is the number of orbitals in n equals to 4? So you need to understand, when I say n equals to 4, means it is your fourth orbit. It is your fourth orbit, right? And for n equals to 4, what are the possible values of L? It can be 0, 1, 2, 3. So for n equals to 4, possible values of L are 0, 1, 2, 3, means S, P, D, F. Means what? In the fourth orbit, we have total 4 subshells: 0, 1, 2, 3, S, P, D, F, right? But we have to count number of orbitals, right? Now, in each subshell, S, P, D, F, these are your subshells. These are your subshells, correct? Now, in each subshell, we have certain number of orbitals, and that we can get by the values of m, right? So for S or L equals to 0, the value of m is what? 0. For L equals to 1, the possible values of m are -1, 0, +1. For L equals to 2, the possible values of m are -2, -1, 0, +1, +2. And for L equals to 3, the possible values of m are -3, -2, -1, 0, +1, +2, +3. So you can see that For 0, we have one value of m. For 1, we have 3 values of m. For 2, we have 5 values of m. And for 3, we have 7 values of m. And each m value indicates an orbital. So these are your number of orbitals. Students, in any of the s subshell, you have one orbital whose m is 0. In any of the p subshell, you have 3 orbitals whose m is -1, 0, +1. For any of the d orbital, you have 5 orbitals in it, -2, -0, +1, -2, -1, 0, +1, +2. And for any of the f subshell, you have 7 orbitals in it whose m values are -3, -2, -1, 0, +1, +2, +3. So in n equals to 4, I will have total 4 subshells, and inside that I will have total 7 plus 5, 12 plus 3, 15 plus 1, 16. I will have total 16 orbitals. Inside n equals to 4, I will have 4 subshell and total 16 orbitals. So like this, you can count the number of orbitals, and always remember that each orbital has 2 electrons, maximum of 2 electrons in it. So total number of electron in n equals to 4 will be 32. But instead of doing like this, we also have formula, right? If n is given, so for any n, the number of orbital can be calculated as n square. At the same time, number of electron can be calculated as 2n square. Number of orbital n square and number of electron as 2n square. And just like n equals to 4, you can do it for any n value, 3, 2, 1, anything. Right? And now I hope that you will always remember that in each subshell, what is the number of orbital, and it is fixed, right? It will never change. Whenever you have a f subshell or L equals to 3, right? So for f subshell or L equals to 3, the number of orbital will be always 7. For D, number of orbital will be always 5. For P, always 3. For S, always 1. So from this, you can understand how we can count number of orbitals and number of electrons, right? And I hope now you have understood that SPDF, they are nothing but your subshells. And within those SPDF, you have your orbitals. Later on, I will tell you, those orbitals also, they have name. Like in S subshell, we have orbital whose name is S only. In the P subshell, we have 3 orbitals, right? And these 3 orbitals are named as Px, Py, Pz. In D, we have 5 orbitals. Their names are dxy, dyz, dxz, dx square minus y square, dz square, and so on. Right? Now, in the quantum model, right, the next part is electronic configuration. And when you say electronic configuration, you need to understand one thing. In the electronic configuration thing, we have 2 parts. We have 2 aspects of it. First, we need to understand how we can distribute electron in the subshells. Subshell means SPDF. And then in the electronic configuration only, we need to understand how we can distribute electrons in the orbitals, right? Orbitals means in the book, you will find it as orbital diagram. In your book, the name of the topic will be orbital diagram when you distribute electrons into the orbitals. But point is, before we start with electronic configuration, we need to understand one thing. What are the concepts that we will be using while writing the electronic configuration? So first point is, electronic configuration means distribution of electrons in the subshells. And currently, we use total 20 subshells. We use total 20 subshells to write down the electronic configurations. And those subshells are 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and from 6 it will decrease again, 6s, 6p, 6d, 7s, 7p, right, 8s. So these are the 20 subshells you have, and with each subshell we always represent its orbit number just to avoid any confusion. Like you will wonder why we write 1s, although the subshell is s. We write 1 always or 2 always to indicate that whose part it is. This is the S subshell of first orbit. This is the P subshell of second orbit. This is the D subshell of third orbit. This is the F subshell of fifth orbit. So when we represent subshell, we always write its orbit number along with the subshell. Subshell is F, but its orbit number is 5. Now, in these subshells, in these 20 subshells, when we distribute electron, so that concept is called as what? Electronic configuration, right? And for that, we use certain rules, certain laws, right? Like whenever you distribute electrons in your subshells or orbitals, right? So that is done according to Aufbau principle. That is done according to Aufbau principle. What your Aufbau rule says? Aufbau rule says electron will first enter or distributed in that subshell or orbital which has lower energy, So Aufbau rule says that when you are distributing electrons in the subshells or orbitals, so first you need to put electron in that subshell or orbital which has lower energy, right? Now, out of these 20 subshells, first we need to know that which subshell has lower energy. Like, I hope some of you know already that 1s has the lowest energy, then it is 2s, then 2p. But point is, for all these 20 subshells, if you want to know the energy sequence, that which one has lower energy, which one has higher energy, so for that you have to follow another rule. That is called N plus L rule. Right? So let me first tell you what is the meaning or what is the use of N plus L rule. First of all, N plus L rules helps you in comparing the energy of subshells and orbitals using the values of N and L. What it says? It says that higher the value of N plus L, higher is the energy. Means, suppose if I take 2s and 2p subshells, so out of these two I have to compare which one has more energy, which one has less energy. So I will have to just find the value of N plus L. For 2s, N is 2, and for s, L is 0. So N plus L is 2. And for 2p, N is 2, and for p, L is 1. So it is 3. Now clearly for 2p, the N plus L value is large, right? So the one whose N plus L value is large, that will have more energy. So out of 2s, 2p, I can say that 2p has more energy than 2s, right? Sometimes what will happen, you will get same value of N plus L. If N plus L values are equal, then the one with higher value of N, higher N, will have more energy. Done? Like for example, suppose if I take 2p and 3s, right? So for 2p, N plus L will be 2 plus 1 means 3, and for 3s, 3 plus 0, it is 3. So for 2p, 3s, we are getting the same value of N plus L, that is 3. Now in that case, when your N plus L values are equal, the one with more N value, right, will have more energy. So out of 2p, 3s, 3s has more N value, it is 3. So definitely here, 3s will have more energy than 2p. So using these 2 points, right, first compare N plus L, the one with more N plus L will have more energy, and then compare with N. The more N, more is the energy. Now using these 2 points, you can easily compare energy of each and every subshell, right? But if you don't want to use N plus L rule, then to arrange that subshell, we have a trick, right? And I hope many of you already know that. Just write it down like this: 1s, then 2s, 2p, then 3s, 3p, 3d in sequence, shell number wise, then 4s, 4p, 4d, 4f, then 5s, 5p, 5d, 5f, then again it will decrease number of subshells, 6s, 6p, 6d, 7s, 7p, 8s, right? And to get your energy sequence, just cross them, cut them diagonally, right? lowest energy is for 1s, then it is 2s, then it is 2p 3s, then it is 3p 4s, then it is 3d 4p 5s, then we have 4d 5p 6s, then we have 4f 5d 6p 7s, and then finally we have 5f 6d 7p and 8s. So using this trick you can easily write down the sequence of energy, right? It will be 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p and 8s, right? Once you are done with your sequence of energy, using Aufbau rule, you can easily write down the electronic configuration. Because what we have to do, we have to just distribute electron according to the Aufbau rule. And for each and every subshell, the maximum number of electron that can be accommodated is fixed, right? Like whenever you have a S subshell. So S subshell has one orbital. One orbital can have maximum of 2 electron. So S subshell will have maximum 2 electron. If you have any P subshell, so P subshell has total 3 orbitals, and 3 orbitals can have total of 6 electron. So any of the P subshell, it will have always 6 electron, maximum 6 electrons in it, and it will increase by 2, like when increase by 4, not 2. When you go into your D subshell, so 6 plus 4 it will be 10. If you go into your F subshell, it will be 14. So these are the maximum number of electrons that any subshell can accommodate. S can have 2, P can have 6, D can have 10, or F can have 14. Now from this, we can easily write down the electronic configuration of atoms. Students, let's take few examples. Like if I talk about sodium, and I have to write down the electronic configuration of sodium. So for sodium, atomic number is what? 11. And I have to distribute 11 electrons into those subshells. So lowest energy is for 1s. 1s can have maximum 2 electrons in it. Then 2s, it can have 2 electrons in it. Then 2p, it can have 6 electrons in it. And up to this, we have filled 10 electrons, 2 plus 2 plus 6. Now we are left with only 1 electron. And the next subshell is 3s, so it will have 1 electron. So 1s2, 2s2, 2p6, 3s1 is your electronic configuration for sodium atom. Likewise, you can write it down for any atom. If I do it for Fe, whose atomic number is 26, right? So it will have 26 electrons, and I will have to distribute those 26 electrons into the subshells, right? So 1s, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 4s, 2. Up to 4s, 2, you are done with your 20 electrons. 2 plus 2 plus 6, 10. 2 plus 6 plus 2, 10. So now we have filled 20 electrons. So we are left with 6 electrons. And the next subshell is 3d. 3d can have maximum of 10 electrons, but we have only 6 electrons. So in 3d here, it will be having 6 electrons. So this is your electronic configuration. Like this, you can practice, you can write down electronic configuration for all those atoms whose atomic numbers are between 1 to 30. Because at least from atomic number 1 to 30, you should know in this chapter, because that is in your syllabus, right? But at the same time, please remember that copper and chromium, these two are the atoms in between 1 to 30 atomic number. So copper and chromium are the atoms, right, in which Aufbau rule is violated in the last two subshell. In the copper, in the last two subshell, right, the configuration is 4s1 3d 10, and for chromium it is 4s1 3d 5, and that happens because of half filled and full filled configuration. Later on I will tell you that. But please remember that copper, chromium, they violate the Aufbau rule. Now, after writing electronic configuration or distributing electrons in the subshell, we have to learn one more thing here along with this. That is orbital diagram. You know, in orbital diagram, what we do, we represent orbitals by square boxes. We represent orbitals by square boxes. For each orbital, you draw one square box. And we represent electrons by arrow. Electrons by arrow. Right? Like for example, in iron, for this 3D subshell, if I have to draw the orbital diagram, so in D subshell, I have total 5 orbital, right? So for 5 orbital, I will draw 5 square boxes, 1, 2, 3, 4, 5. So this is the orbital diagram of D. In the same way, if you draw it for P, you will have 3 square box, for S 1, for F 7. And in these orbitals, you can represent electron by arrows. But point is, when you go and distribute electrons in these orbitals, you need to follow two more rules, right? One is Hund's rule, right? And another one is Pauli exclusion principle. Pauli exclusion principle. Hund's rule says that when you distribute electron, the total spin should be maximum. Or in simple words, you can say like this, according to Hund's rule, if I go, so each orbital should get one electron first, then only pairing will happen. Like in this case, if I have 6 electron and I distribute electron according to Hund's rule, so I cannot pair before filling one electron each in the orbital. I have 6 electron, so first I will give one electron here, then second here, then third here. I cannot do pairing, right? I cannot do pairing before giving one electron each in the orbitals. This is your Hund's rule. So for 6 electron, you can do it like this, 1, 2, 3, then 4, then 5, right? After 5 electron, each orbital has one electron, right? So one electron is left. Now you can do pairing, right? The 6th electron will enter here, and you can notice that when I distributed the second electron in this orbital, right? So I have done it by drawing it in a downward arrow. So this downward arrow indicates opposite spin. If the first electron has plus half spin, that means the second electron will have minus half spin. In an orbital, both electrons cannot have the same spin, right? And that point is nothing but your Pauli exclusion principle. So when you distribute electrons in the orbital, you use these two, Hund's rule and Pauli exclusion principle, right? In the same way, you can do orbital, you can draw orbital diagram of any, right? If I draw it for 3s, in 3s I have one orbital, so one square box. Here we have one electron, so only one arrow, right? So along with electronic configuration, you need to know how to draw the orbital diagram, right? And till now, we talked about only atoms, right? And I guess we have already discussed about the orbital diagram, right? Still, I am writing it once again. S subshell can be represented by one square box. P can be represented by 3 square box because it has 3 orbital. D can be represented by 5 square box because it has 5 orbital, and F can be represented by 7 square box because it has total 7 orbitals, right? 1, 2, 3, 4, 5, 6, 7. Done. And in those orbitals, in those square boxes, electrons are filled with help of arrows. Electrons are represented by arrows, right? And we always use Hund's rule and Pauli exclusion when we distribute electron in the orbitals, correct? So now we should discuss a little bit regarding the ions, how you write electronic configuration of ions, especially the cation, because for anion you can follow the same concept that you use for normal atoms, but in case of cations, you cannot write down electronic configuration directly. Whenever you have to write down electronic configuration of an cation, first you need to write down the configuration of parent atom. Like suppose if I have to get electronic configuration of Fe2 plus ion, so I cannot write it directly. I will definitely get wrong answer. For Fe2 plus, I need to write down the electronic configuration of Fe first. It is, just now I wrote 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d6. Now when I go from Fe to Fe2 plus, that means I need to remove 2 electrons. Now electrons are always removed from the outermost shell, not from the highest energy subshell, because here the highest energy is for 3d, but the outermost shell is what? 4th one, right? So in this case, if you remove electron, so that will be removed not from the 3d but from the 4s, because 4s is the outermost orbit here, and we have to remove 2 electrons, and 4s has 2 electrons in it. So those 2 electrons will be removed. Then for Fe2 plus, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s0 and 3d6. So now I hope that you have understood how you can write the electronic configuration of both atoms and ions, right? But for ions, especially the cation part, always write down the electronic configuration of parent atom first. For anion you can do directly, right? For anion you can directly do the total count of electron, and you can distribute electron. But always be careful when you write electronic configuration of cation. So now we are done with electronic configuration and orbital diagram as well. So let's see another part of this quantum model, because in quantum model you can say like this, we have two parts. In one part you talk about quantum numbers, energy, electronic configuration, and in the other part, right, you talk about shapes of orbital. So first you need to know that orbital is the 3D space in your atom where you have a maximum probability of finding electron, where there is a maximum tendency that you can find an electron. And because they are 3D spaces, so we need to know how they look, right? We need to understand what will be the shape of orbital, correct? So if you talk about shape of orbital, so that we get from the azimuthal quantum number. First of all, that information we get from azimuthal quantum number, right? Because the one whose L value is 0, or if your orbital is S, then its shape is what? Spherical. If your orbital has L equals to 1, it is P, then your shape of orbital is dumbbell. And if your orbital has L value 3 or D, then you have double dumbbell. That's why you will see in books it is written that shapes of orbital, the information regarding shapes of orbital we get from azimuthal quantum number. That's the application of azimuthal quantum number. And if you talk about application of principal quantum number, so from principal quantum number we get two things, we get two informations. First, energy, right, and then size of orbital. Shape of orbital we get from azimuthal quantum number. On the other side, the size of orbital, right, is determined by the value of principal quantum number. Higher the principal quantum number, larger will be the size of orbital. So shape from azimuthal and size from principal. Now one by one we will see some of the orbitals, their shape, which is present in our syllabus. Like we have to talk about the shape of 1s orbital. 1s orbital is very easy, it's spherical, and these dots that I am drawing, right, so these indicates that here you have probability of finding electron. In these regions you can find electron, right? If you talk about the shape of 2s orbital, so 2s is also spherical, 2s is also spherical, but it is bigger than your 1s orbital. 2s is bigger than 1s because n is more, and it is spherical, no doubt, but in 2s orbital you will notice that these are the regions in which you can find electron. These are the regions in which you can find electron, but between these two regions there is a gap. In these regions, right, in this region you can't find electron. So this region is called node. More precisely, this is your radial node here. This is your radial node here. So basically node is that space in which probability of finding electron is 0. And probability of finding electron, or probability density, in terms of wave function, it is written as psi square. So initially I told you that psi has no physical significance, but the square value of psi, that means psi square tells you the probability of finding electron. So psi square is nothing but your probability density. So these regions, right, here we will have some values of psi square, right, from 0 to 1 in terms of probability, and not 1, because even in the orbital, even in the region of orbital, we have maximum of 90 to 95% chance that we can find an electron, not 100%, right? And in this 2s, these are the regions where you can find electron, right? But in this region there is no electron, so we call it node. And in the node part, the value of psi square, the value of probability density will be 0. Psi square will be 0 in the region of node. In the same way, I hope you can draw 3s now, right? 3s will be spherical, it will have 3 regions, and it will have 2 node. right? But if you talk about the shape of p orbitals, right? So p starts from the second orbit. In first orbit, we do not have p subshell or p orbital. So p starts from where? Second orbit, right? And inside p subshell, we have three orbitals. It is 2px, 2py, 2pz, right? All of them, they have dumbbell shape. The only difference in them is orientation, their position, right? The shape of 2px orbital is like this. If this is your x-axis, this is your y-axis, then the shape of 2px orbital is the orbital, or this is called lobes, right? This is one lobe, this is another lobe. The lobes of orbital will lie along x-axis in case of 2px orbital. So similarly, in case of 2py orbital, right, you can guess it now, right? If it is your xy axis, then in 2py, the lobes of orbital will lie along your y-axis. And similarly, in case of 2pz, I'm not drawing that, you can do it by your own, right? In case of 2pz, the two lobes of dumbbell, they will lie along your z-axis. So that is the shape of your 2px, 2py, 2pz orbital. And in the same way, you can draw 3px. In 3px, what you will do? You will draw another concentric dumbbell here, right? In between, you will have another radial node. So only the radial node will increase by increase in your shell number, orbit number, right? The most important shape is for our d orbital, and that we get very frequently in the NEET. And d orbitals start from the third shell, and inside d subshell we have 5 orbitals. Their names are 3dxy, 3dyz, 3dxz, correct? Shapes of these three are quite similar. Like when you talk about 3dxy, so if this is your xy axis, then in d orbital we have two dumbbell, and those two dumbbells or those lobes will lie in between the axis at an angle of 45 degree. So this is one dumbbell, this is another dumbbell, right? So those two dumbbells will be in between xy axis. So two dumbbells in between xy axis is dxy. Similarly, two dumbbells in between yz axis is your 3dyz orbital. Two dumbbells in between your xz axis is your 3dxz orbital. But the shape of 3dx square minus y square and 3dz square is little bit different. In case of 3dx square minus y square, again you have two dumbbells, right, xy axis, but in 3dx square minus y square, those lobes, they lie along the axis. In 3dxy, the lobes are in between the axis, but in case of dx square minus y square, those lobes are along your x-axis and y-axis. Similarly, in dz square also, if this is your z-axis, your dumbbell will be along the z-axis. But dz square is completely different, because in dz square, we don't have two dumbbells. We have a dumbbell, and then we have a small spherical circular region here around the center. So dz square is completely different, right? Now these shapes you need to remember, because you get questions from it. They will ask, in which orbital lobes are along axis, in which orbital lobes are in between the axis. So those types of questions you can predict that you will be getting in your NEET examination. So now, after understanding, right, what is your shape of orbital, I told you that the region in which probability of finding electron is 0, that is called node. But those nodes are classified into two types. One is called radial node, because it is spherical in shape, and one is called angular node. It has a conical shape. And these two nodes you can calculate directly from the formula. Radial node is n minus L minus 1, principal quantum number of the orbital, minus azimuthal quantum number of the orbital, minus 1. And angular node you can calculate simply by L. It's directly equals to azimuthal quantum number. And if you calculate total number of nodes, so total nodes will be angular node plus radial node. So n minus L minus 1 plus L, it will becomes n minus 1. So for any orbital, if they ask calculate the number of radial node or angular node, you can do that, right? Suppose I take this 4f. I take 4f orbital. In 4f orbital, if I calculate radial node, so radial node will be n is 4 minus 4f, L is 3. Okay, instead of 4 I wrote 3. Let me correct that. For radial node, for 4f, n is 4 minus 4f, L is 3 minus 1. So it will be 0. And if you talk about angular nodes in this, right? So angular node is directly equals to L. So for f, L is 3. So in this case, your angular nodes will be 3. So for any orbital, you can easily find out what is radial node, what is angular node, right? And if I tell you, if I explain you this from the shape, so from shape you can understand like this. From the center, when you go outside towards the boundary of the orbital, so when you go radially outward, in between if you find a node, so that is your radial node. That is your radial node. And if you look at these p subshells, so here if you take an axis and you change angle, right? So by changing angle, if you get a node, so that is your angular node. So in p, this portion, which looks like a ice cream cone, right? This whole part is a node, right? 2 ice cream cones, you can say. So these 2 ice cream cones are like your angular nodes. So in each p subshell, in each p orbital, you can see that you have one angular node. And in case of d, you can have 2 angular nodes or 2 ice cream cones. Like if I consider 3dx square minus y square. So this is one of the angular node, right? And this is another angular node we have here, this one, right? Yeah. So for S, angular nodes are 0, for P, angular nodes are 1, and for D, angular nodes are 2. Correct? One more thing, from these angular nodes, if you pass a plane on which electron density is 0, suppose that this is an angular node, and from here if I pass a plane, so on this plane also electron density will be 0. So these planes are called as nodal planes. So this is another term we have here. The plane passing through angular node on which electron density is 0, so that is called your nodal plane. Mostly number of nodal planes will be same as number of angular node, except 3D z square. In 3D z square, you cannot pass a plane, right, on which electron density will be 0, because in 3D z square, on the center we have this spherical region, right, and the plane will always pass through this. So the plane will always have some chance of getting electron. So from 3D z square, you cannot have a nodal plane. The nodal planes will be 0. Now, after radial node, angular node and nodal plane, let's talk about a final point in this chapter, which is basically a graph, but sometimes you get question from this. Students, we have 3 parameters, graph of 3 parameters in this chapter which we need to focus. One is graph of wave function, one is probability density, and one is radial probability, right? Like if you take 1s orbital, right? So for 1s orbital, if you draw the graph of wave function with radial distance, right? So it is like half of the wave. It is like half of the wave, like this. Not half, you can say quarter wave. Full wave is like this, right? So this is half wave and this is quarter. This is quarter. So the graph of psi for 1s, it is like a quarter of the wave. And this is the positive amplitude. And if you draw the same for your 2s orbital, again psi versus r. So for 2s orbital, it is like positive and negative, both amplitudes, plus and minus, right? And if you do it for 2p orbital, so for 2p orbital, the graph of psi versus r is, here it will be half of the wave, not quarter, like this, plus half. So these are the graph of your wave functions psi for 1s, 2s, 2p orbital. For these three orbitals, you need to remember these graphs because they will directly ask this in your examination. Now from the psi, we can easily plot graph of probability density, that means psi square. Psi square. So in psi square what will happen? The positive part will remain as it is, but the negative part will also become positive. So in 1s you can notice that we have only positive values. So in psi square also it will be same, right? But in case of 2s, if you notice, when you plot psi square, what will happen here? The positive part will remain as it is, but this negative part will become positive, because square functions can never be negative. And again in case of 2p, because the psi values are always positive, so here also the graph of psi square will remain same as it is. So from psi to psi square we have change only in the 2s orbital. The negative part become positive. Now if you draw the radial probability is basically denoted by 4 pi r square psi square. So if you draw the radial probability, so radial probability tells you that in a certain volume, in your atom, in an orbital, if you take a small volume, so in a small volume, in a small space, what is the in that space, what is the probability of finding electron? So that radial probability is basically volume of that space multiplied by probability density. So that's why we write 4 pi r square dr into psi square, and that will be very easy for 1s. It's like half of the wave. And you know what it indicates? What is the meaning of radial probability? In the graph of radial probability, you notice that here you have the maxima value. And for hydrogen atom, this maxima value you get around 0.529 angstrom. This is the radius of the first orbit of the hydrogen atom. Means what? Even it is quantum model, even we are talking in terms of probability, still we are saying that probability of finding electron, right, of the 1s orbital is highest near the first orbit at the distance of 0.529 angstrom. So that radial probability tells you that from nucleus, when you go at certain distance, so at that distance, at that volume, what is the probability of finding electron, right? In case of 2s orbital, if you check the radial probability, it is also denoted by r, or 4 pi r square psi square. The radial probability will be something like this. Two maximas, but amplitude will increase here. So means what? When you have an electron of 2s orbital, right? So probability of finding electron of 2s is higher near the second orbit and lower near the first orbit, right? And for 2p, even the graph of radial probability remains same. Means what? The electrons of 2p orbital can be found mostly near the second orbit, or the distance of the second orbit. So that radial probability tells you at what particular distance what is the probability of finding electron. And radial probability is basically a multiplication of unit volume, elemental volume, into the probability density. And these graphs are very important for your examination. So now, as we have discussed the quantum model, in quantum model you have mainly two things: configuration, electronic configuration, and the orbital part, shape, right, wave function, radial node, angular node, and these graphs, right? So let's now discuss some of the questions from this quantum model. Let's see what type of questions we get in the examination from this quantum model part. So take your pen paper along with me. You also try to do these questions. First question is the quantum numbers. If you want to do by your own, pause this video, solve it, later on match your answers, right? Okay, so the question is the quantum numbers of 4 electrons are given below, the correct decreasing order of energy. So we have to just compare the energy of electrons, and their quantum numbers are given. So you know that it is a direct question of n plus L rule. N plus L rule, N plus L rule. So 1, 2, 3, 4, right? The quantum numbers are given. N4, L2 means n plus L, 4 plus 2 is 6. N3, L2, 3 plus 2, 5. N4, L1, 4 plus 1, 5. N3, L1, n plus L will be 4. So clearly, highest n plus L we have for the first one, and lowest n plus L we have for the fourth one. So highest energy will be for the first and lowest energy will be for the fourth. And now for these two, n plus L are equal. So we do compare that by value of n. Here n is 3, here n is 4. So n4 is greater. So third will have more energy than the second one. So order will be 1, then 3, then 2, then 4. 1, 3, 2, 4. 1, 3, 2, 4. 1, 3, 2, 4. B. So very easy, like just use of n plus L rule. And this question we got in the NEET 2024 examination, right? Direct question from L plus L rule, right? And of course here your answer is nothing but B. That means 1, 3, 2, 4. And we just did that by n plus L rule. Now let's move further. Let's see more questions from this. Can we do this matching? Match list 1 and 2. On the left hand side, we have quantum numbers. On the right hand side, we have the informations provided by that quantum number. Correct? So, this is your ML. ML means nothing but magnetic quantum number. MS means nothing but your spin quantum number. Magnetic quantum number is also written as M subscript L. L is your azimuthal quantum number, N is your principal quantum number. So here we have shape of orbital. Just now, while discussing shape of orbital, I told you that shape of orbital we get to know from the azimuthal quantum number. So C should match with 1. Size of orbital, the information of size we get from principal quantum number. So D should match with 2. Let's match these two first. C with 1 and D with 2. C with 1 and D with 2. Only one option is there in which C is matched with 1, D is 2. Now definitely if you talk about A and B, so A has been matched with third one. Orientation of orbital. Definitely the magnetic quantum number tells you the orientation of orbital. And spin of electron, I told you repeatedly that we get to know this from spin quantum number. One thing you can notice here that magnetic quantum number we represent that by M as well as M subscript L, and spin quantum number we represent by S and also M subscript S. So do not get confused by that. So in this case definitely the answer will be D, right? Yeah, it is D. And again this question we got in the NEET 2024 examination. So what are the applications of each and every quantum number? From that also we get questions, right? Principal quantum number tells you about energy and size of orbital, right? Azimuthal quantum number tells you regarding the shape of orbital. Magnetic quantum number tells you about number of orbital and orientation of orbital. Spin quantum number tells you regarding the clockwise or anti-clockwise spin of electron. So the next question we have is incorrect set of quantum numbers from the following is. So if you notice, this question is based on the condition of quantum numbers, right? I told you that azimuthal quantum number depends on principal quantum number. Magnetic quantum number depends on what? Azimuthal quantum number. So from that we have this question. If you notice carefully, so if n is 4, L3 possible because L should be smaller than n. And if L is 3, then M can be minus 3 2 plus 3. Because M is minus L2 plus L, and spin quantum number can be minus 1 by 2. So first set is correct. If you look at the second set, if n is 5, L is 1, that's possible, right? Because L should be smaller than n. Now if L is 1, M cannot be minus 2 2 plus 2, because M should be always minus L2 plus L. It should be minus 1 2 plus 1, right? So definitely in the B set, after L, the values of M are not correct. It should be minus 1 2 plus 1. So here answer should be B. Answer should be B. Correct? Now, can we do this question, a statement based? The value of wave function depends upon the coordinates of the electron in the atom. The value of wave function depends upon the coordinates of the electron in the atom. And the second statement is the probability of finding an electron at a point within an atom is proportional to the orbital wave function, right? If you notice, if you read the statements carefully, so here definitely your answer will be A. Statement 1 is true, but statement 2 is false. Why? Because, please notice here, the probability of finding electron at a point within an atom is proportional to the orbital, not wave function, but square of wave function. Wave function has no physical significance, right? It is proportional to what? Square of the wave function. But the first statement was absolutely fine. The value of wave function depends upon the coordinates of the electron, and those coordinates we can observe that in the mathematical expression of that wave function, right? So statement 1 was true and 2 is false, and that's why the answer is definitely A. 1 is true, 2 is false. And this question we got again in NEET 2023. So we get statement type question also, right, in the atomic structure. So now I hope that in this chapter you can classify the whole chapter into 3 parts. When you do revision, right, after this session, so you can classify the whole chapter into 3 parts. One part Bohr model, one part dual nature, and one part quantum model. The Bohr model you can further classify into parameters of atom, electron, orbital, orbit, and the second part will be radiation, spectral line, Rydberg equation. In the dual nature part, now what you can do in the revision, you can combine all the wave topics, wave related topics, like parameters of wave, right? Photoelectric, black body radiation, de Broglie's equation, Heisenberg uncertainty principle, all those concepts you can combine and you can call it as dual nature. And in quantum model, you know that quantum numbers, their condition, electronic configuration, orbital, shape and graph of wave function, right? The meaning of psi square, 4 pi r square, psi square. And if you do that much, right, and if you solve all those DPPs that we are providing with the video itself, right, you can find that in the description, and also you can get that on the PW app easily. So download the PW app, and from there also you can find those DPPs. So if you complete those DPPs after watching this video completely, believe me, you can solve each and every question of the atomic structure chapter, right? So thank you so much. Keep preparing, because consistency is the key of success, right? Over and out. Bye bye. Take care.